Welcome to this course in which we shall be mastering image segmentation by building a virtual outfit changer plugin with the FiftyOne app. The tool we shall build will take in as input this image and then output this other image based on a given prompt. So as you could see here, we are able to modify the boot color based on just this prompt and an inpainting model. Nonetheless, for the inpainting model to produce this new output where we have the boot color which has been changed, it takes in the prompt, as we've said already, and a mask. And in order to generate this kind of mask where we have all the other parts apart from the boot which are set to a pixel value of 0, we are going to train our own Segformer model, which is going to get this input and generate a mask like this one, from which we could extract specific classes, like in this case, the boot. And with that said, we'll start by looking at data preparation. Then we'll go on to dive into model creation. Then we'll train our model. And after training this model, we would make use of this trained segmentation model to input masks like this into our inpainting model, such that we are able to generate new images which have been modified based on a specific prompt. Apart from using this tool as a virtual outfit changer, we are going to make use of it in data augmentation by creating a very simple plugin with the FiftyOne app. The FiftyOne plugin we'll build is quite simple and straightforward. The first thing we'll do is select a given sample. Once this sample is selected, we'll go on to click on Stable Diffusion Inpainting plugin and then put in the different values like the specific class. Like in this case, we want to modify the shirt. We'll also select number of augmentations. We'll pass in the prompt. We would have the number of inference steps. We would have the guidance scale, and then we would click on execute. Once executed, we'll wait for a little bit, and then we get our generated samples like this one we have right here. We go from an input where this man was putting on a military green shirt to one where we have this man putting on a designer shirt. And with that said, let's dive into data preparation. Now we understand the problem we're trying to solve. We'll go ahead and download our data set. So first things first, we'll head over to Kaggle, where we're going to make use of Raj Kumar's data set entitled the People Clothing Segmentation data set. That's all the images of people and semantic segmentation masks of their different clothings. If you scroll down here, you'd see this JPEG images and the corresponding JPEG masks, same as the PNG images and the corresponding PNG masks. So this is the data set we are going to be working with, which also comes with this labels CSV file. In this labels CSV file, we have all the different classes which we are going to use in our data set. So we go from accessories right up to wedges. So we have 59 classes, including this null, that is to say we have the background. Now, if we scroll back up here and we open this up, you find that for every image, as we had said already, we are going to have a corresponding mask. So this is image 0001. If you open this up, you have this image of this lady, and then reduce this and check out this corresponding mask. So open this up, we have, there we go, we have its corresponding mask. In summary, for every pixel point in the image, there is a corresponding point in the mask, and there's different images and masks are stored in different folders in our data set. Before we proceed to download this data set, we should note that it contains 1,000 images and segmentation masks pairs of individual people's clothing and 59 object classes, which we had seen already in the labels CSV file. Then also we could go ahead, click on settings, we scroll down, and then we click on create new token. Once you click on create new token, you would have a cargo.json file, and once you have this cargo.json file downloaded, you then go ahead and upload it to Google Colab. So this is our cargo.json file right here. And now we install Kaggle. We are going to make this new directory. We're going to copy our cargo.json file into our Kaggle directory. Then we'll finally download our data set. Let's get back. Let's go back, and then we copy this command. So here we have, let's reduce this so you could see it clearly. So we have copy API command. So if you copy this and then you paste out, let's just paste this out down here. If you paste this out here, you see you have Kaggle datasets download, and then you have the owner, that's the creator of this data set, and then you have the dataset name. So that's it. We run this cell, and then given that the output or what we are going to download is going to be this zip file, we are going to unzip this into our dataset folder. After the downloading and unzipping is done, we open up this files, and then you could see that we have this people clothing segmentation.zip file, and then we have in our dataset folder, we have exact same folders we had seen already in this Kaggle dataset or on the Kaggle platform itself. So right here we have images, we have the masks, and then we could now prepare this dataset. In the section on data preparation, we will start by splitting the data. That's creating a train and validation data set. Then we'll pre-process this data, visualize this data, and finally we are going to make use of Voxel 51 for a much better visualization. Diving into the splitting of our data set, we have this paths which we're going to create. So we have the train path, which will simply be the image path. So here we have image path, and let's copy the path, or let's just copy this. No need to open that up. So we copy it and paste it in here, and then we'll also copy the annotation path, that's a masks path, and paste out here. So we have annotation path. There we go. We copy from here and paste in the cell, and then we are now going to create our validation path. So let's just copy this and then modify it slightly. Val dataset, and instead of im path we have the val image path, and then the val annotation path. Okay, so that should be fine. This looks fine. We have images, this should be masks actually. So let's copy this again, copy and paste it in here. There we go. And then we also paste this in here. So this, oops, take this off and paste it in here. So we have val dataset there. Okay, so this is our different paths. That's the image and or the train and the validation paths. With these paths defined, the next thing we want to do is create this validation dataset directories. So we have the val dataset directory which we're going to create, and then we also have the PNG images directory and the PNG masks directory. So it's just going to be similar to what we had already from this original dataset. So now this two here will be for our train, and then the other two will be for the validation. Let's run this, and there we go. So let's refresh and then see what we get. So here we have our data set, which is actually our train data set, and then here we have the validation data set. If we open this up, you see we have PNG images and PNG masks. That's fine. Now the next step we want to carry out is define or pick out randomly some images from our train data set and then move them to our validation dataset folder. Now let's select this. We randomly picked out this list of images. If you open up this file or you open up this folder and here you would find that all the images and even the masks take up this format. You can see how we have the image underscore the number, which is one of this, and the PNG. So that's the formatting of all our images and even the masks. So if we open up this mask here, you should be able to have that same format. Here's img underscore number.png, and with the mask is seg instead of the img. So that's the only difference. Let's now use the short tail tool to move these files or these images from this original folder to the validation folder. So we'll start by importing short tail. There we go. Once we import that, we could now make use of it. So we'll do for all the different elements in here. So for path or for name in val list. So for name in val list, we are going to do short tail move, and then we'll specify the initial path and then the final path. Okay, so our initial path in a case like this, let's suppose we had 0001. So if we had 001 or 0001 as an example, we want to have this path. Let's take this, that's image path, because up to this point this is the path. So we have image path, then we'll just simply write here in path. So we want to have this path, and then we also want to have img underscore, so take this off, plus the name, because we're going through this list. So plus name for a specific name in that list, and then plus dot png. Okay, so that's it. And then for the final path, final destination, let's copy this and paste out here. For our final destination, we would have instead val image path, and then we'll also have image underscore name dot png. So that's how it's gonna be. And then now we'll just do the same for the annotations. Remember the annotations, we had seg instead of image or instead of img. So here we have anno path, and then here we have anno path. Okay, so let's take this off. We now have seg, and then here we have seg. Then let's run this and then see what we get. We are getting an error. Let's look at this. When we look at this, you see there's no the errors showing no such file or directory as this here. We see that there's this slash which we omitted. So let's slide up and then modify here. Just add the slash, and then we rerun again. So we have here slash, and then here slash. Run again and move these files. We still have another error. And this time around, we notice also that we omitted this images folder in our PNG images folder. So getting back up, we just need to make this directory. So we have images, and then we also have masks. So masks. Okay, so that's it. Let's run this again. That's already been done. And then now let's move. We have the files which have been moved, as we could see here. If we click open images right here, you could find these files. Now the next step will be to create a TensorFlow data set. So we'll have our train data set, which is going to be our TensorFlow data set made of the different file paths. So let's go ahead and do that from tensor slices. And then the way we will define this is such that we have this image or the path of an image and its corresponding annotation. So here we have in path, that's image path, and then for I in the image list, that's in the list of all our images. So we have image path, and then we'll also have the annotation. So this is the first slice, and then our second slice here we have annotation. Let's just put it below. So copy this and paste here. So here we have annotation, annotation, and annotation. So for every element in this TensorFlow data set, we have an image path and its corresponding annotation path.
Let's run this and let's do for I in train data set. Let's take an element and then we print it out. Well, we're having an error, so let's get back up here and see why we're getting this error. Here we have list object has no attribute is identifier. Now let's get back and try to see where we made an error. Looking at this, we forgot to make this a tuple. So this is actually a tuple composed of this input or this image and its corresponding annotation. So let's run this again and see what we get. There we go. You can now see that we have this image or this image path. Let's scroll this way so we could see that image path. We have this image path, and then we also have its corresponding annotation path. And also looking at this annotation path, you'll find that it's different actually. So we should modify this. Here we have 0987, whereas here we have 0336. This means that looping through the image path and the annotation path, we are not getting the exact same order of the different elements. That's the different images and the annotations. So that said, instead of looping through the annotation path here, we'll want to loop through the image path. So we'll still loop through the image path, but since we do not want to have the images but instead of segmentation, what we'll do is we are going to take off part of this I right here. Now let's go step by step so you understand exactly what's going on. So if you do for I in list directory image path, and then you print out I, break. If you print out I, you would find that we have this here, this path, or rather this file name, image as img0336 png. Okay, now the idea here is to take off this img and replace it with seg. So let me get back to this. It's easier to open this up since there are fewer files. So let's scroll down and you see here we have seg. So what we want to do is maintain this path, while taking off this first three letters. So now what we'll do is we'll have I. So if we want to have I, or let's say we take seg, we want to do seg plus, or rather seg like this, seg plus I, which goes from, because this is 0 1 2 3, so it goes from 3 to the end, Okay, run that again and you see we have seg 0336. That's fine. So getting back here, we're gonna have annotation path plus I, but instead of having plus I, we're gonna have plus seg. There we go, and then plus I from 3 to the end. So let's run this again and then check this out. We now see here that we have exact same file. So we have the image and then its corresponding annotation, which matches exactly what we expect. So here we have 0336, and then here we have 0336. We could print out, let's say, 3 others. So we see that all this match because this time around we're taking from the same list. So that's it, 0613, 0703, 0613, 0703. So that's fine. We just replicate this for the validation and we move to the next step. So here we have validation, and then we have val image path. We also have, we have val image path and val image path. Then here we have val image path 2. Okay, so we have the training and the validation sets ready. Could run this, take this off, then we could print out for I in val data set. Let's take a single element. Let's print out I. There we go. We have this now. So here we have image 0049, and then here we have seg 0049, and this is the val data set. whereas here is our trained data set. Let's obtain the length of our trained data set and that of the validation data set. We have len trained data set and then len val data set. There we go. So from here we'll see that if we sum this two up, we should obtain 1,000 different images. And at this point we are going to dive into the next step, which is pre-processing. So we've done the splitting and now we're heading over to pre-process. Talking about data processing, this will be broken up into two parts. The first part will be to normalize our data, normalization, and then the next part will be to carry out data augmentation. So we'll do data augmentation. Okay, so first things first, we would normalize the data. Now we're going to make use of this mean and standard deviations while carrying out normalization. Essentially, for an image, let's say we take an image, what we're going to do is we will take every pixel value, subtract from that pixel value a mean value, and then divide by the standard deviation value. So that's what we're going to be doing. Now it should be noted that these mean values were obtained from the ImageNet dataset. So after the authors of this dataset trained on that or created or built this dataset, they came up with this mean values for the R, G, and B channels. So this is the R, then G, and then B channels. So that's it. So we have this value for R, this value for G, and this value for B. We will go ahead and create our function, which we'll call preprocess. So preprocess. We have our preprocess function, and this function takes in the image and or the image path and its corresponding annotation path. So that's it. And then because we want to obtain the image, so we have our image here. What we're going to do is we are going to make use of TensorFlow's read file method. So we have read file, and then we take in the image path. And then once we finish reading this file, we are also going to decode the file so that we obtain an output image which we could manipulate. So we make use of decode JPEG method. That's after reading our file. And then once we obtain the image, we then go ahead and normalize it. So we have image minus the mean, as we had seen already, divided by the standard deviation. Now we're going to do something similar with the annotation. So we will copy this and then paste out here. Essentially, here we have annotation. There we go. We have annotation. And then here we have annotation path. Remember, the way we created our data set was such that we have the path for the image and then the path for the annotation. So that's it. Let's get back to our function. And then right here, we are going to, before we continue, let's make sure we cast this. So we have our image. We'll cast this into a float. So we have image float 32. And then we will do the same for the annotation. Here we have annotation. We cast it. We have annotation and cast it to float 32. And that's it. So we simply return image and its corresponding annotation. So now we living from the paths to the images and the masks. Let's now create our data set, which takes into consideration this function. So we have our prep train data set, which essentially takes in our train data set, shuffles the data, and then carries out this mapping. So for every element we had in this previous train data set, what we are going to do is we are going to pre-process it and we obtain the output images. Let's run these two cells, and then now we'll do for I. We get an error, mean not defined. Let's get back here and then simply define this. So take this off, run that again, and define that. So that's it. We should be working. Well, we're getting an error again. We are told expected the unsigned int 8 passed to parameter y of up sub, but instead got this of type list instead. Error expected unsigned int, but got 123.675 of type float. So okay, getting back here, we notice that we were supposed to do this after the casting, not before the casting. So running this now should be fine. That's it. And for I in prep, let's say prep train data set, let's take a single element and let's print this out. So let's say ij, so let's print out I and j. There we go. As you could see, we have the image. See, 825 by 550 by 3, so that's our image. And then we also have the corresponding mask, 825 by 550 by 1. Now we want to have this max to be 225 by 550, so we want to take off this last dimension here. So let's get back and then we squeeze that out. We're gonna have after this we have annotation. I'll just put this in here. So we have TensorFlow squeeze. Let's take that off. Want to take off that last dimension, so we'll specify the axis and that should be fine. Let's take this off and run this again. Or we could just check out the shape simply. So let's print out the shape and print out the shape. That's fine. We could see now that we have, let's get back up. We can see now that we have this 825 by 550 by 3 and 825 by 550. We will delve into the data augmentation part where we'll make use of augmentations. So first thing, we'll create our augment method, augment, and then obviously it takes in the image and a corresponding mask, and then we simply get or obtain our augmented image. So there we go. We have this transform which we're going to define shortly, but for now we have this transform which takes in an image. So we have the image and then the mask. Okay, so that's it. And then now what we're going to return is going to simply be our augmented image, which is going to be converted into a tensor. So here we have TensorFlow convert to tensor, and then this takes in the augmented output. But remember that this augmented output is made of the image and the corresponding mask. To understand why augmentations needs to take into consideration both the input image and its corresponding mask, we could consider this figure or this image and its mask which we had already drawn on the board. So here, let's suppose that we want to flip this. So let's flip this horizontally. We'll flip this horizontally. Let's make sure it takes back exact same shape and put this out here. You would find that if you only modify the image and not the mask, then you already have an erroneous data set. So let's get back here, and then we also have to flip this too. Let's flip this, and then you see now that we have this data point, which is exactly what we want. And so that said, getting back to the code with augmentations, all you need to do is to pass in the image and the mask, and then it takes care of all the rest. So you don't need to write any extra code to maybe say whenever you flip the image, you also need to flip the mask. Augmentations does that automatically for you. And here we have the image, and then we'll specify the data type. So here we have data type equal TensorFlow float 32. So our data type is float 32. And then we also here going to return because we return in both the image and the mask. So we have convert to, or let's just copy anyway. Let's just type that out, convert to tensor, and then we have augmented, and then we specify that we want to pick up the mask. So we pick up the mask, and then we specify data type to be float 32. That's it. So now we have our augment method. We could go ahead and define our transforms. That's our augmentation transform. Augmentations is a Python library
which permits developers or AI researchers easily include augmentation in their computer vision solutions. So let's get back here, and then we simply paste this out. There we go. We have this different transforms. We have the transform for the training, and then we have the transform for the validation. With the validation, we are not going to do any transforms, but for the training, we have this random crop. We specify the height and the width, which is 825 by 550, with a probability of 1, meaning that we are always going to have a random crop. We have the horizontal flip. We have the vertical flip with a probability of 0.3, random rotate by 90 degrees. Transpose, sharpening, a random shadow, which we're going to add on the image, and then we have this random brightness and contrast. So that's it. And then obviously for the validation, as we've seen already, it's just the resize. So that's it. And we now run that, and then we have our method right here, which we've just defined. We told h is not defined. We need to define that. So we'll simply have let's just create that here. We simply have the height and then the width, which is not going to be 825 by 550. It's instead going to be 512 by 512, and this is because the model we shall be working with will take this this kinds of inputs. So what this means here is simply that we are always going to take in our input 825 by 550 image and then randomly crop parts of it to obtain then the image which we're going to train the model on. So that's why you have the probability of 1, because we always want to randomly crop out parts of our image. And then because we are always going to randomly crop parts of our image, we don't need to resize because it's already 512 by 512. Now if you take this, or if you change this, let's say to 0.3, let's say there's a probability that sometimes it's not going to be randomly cropped, then in that case you need to resize. So let's take this back. We are always going to randomly crop, and that should be fine. So let's run this cell and then the next cell, and that's it. So we now gotten back to our augment method, and then the next step will be to create a new data set. So as we have seen already from here, we have this preprocessing data set. That's after we've normalizing the data, and then we now move on to our augmented data set. So this is our augmented data set. Before we move on, we are going to repeat this for the validation. Here we have val augment, and then this takes instead the val transform instead of the transform, as in the case of our train or of our augment. So that's it. And then once we get this, we run the cell. Let's go ahead and try to create train and validation data sets. You see we get in this error, image must be a numpy array type. Now that said, we need to create some other method in which we are going to specify that this other methods here, that is augment methods, and the val augment methods contain numpy operations. Remember, here we have this transform, which is essentially made of this different augmentation transforms, and this obviously is done with numpy operations or known TensorFlow operations, and so we need to make use of the TensorFlow's numpy function method to help us work with this numpy functions or with this numpy operations. So that said, we're going to define or redefine some other preprocessing or augment method. It's actually going to be augment. Let's call it the augment, and then here we have image, and then we have its corresponding mask. Then in here we are going to get the augmented output, or let's say, yeah, let's take augmented output. Augmented output is simply going to be the same thing we had here already. So we just define numpy function, and then in here we have the function and we give its name, so augment in this case, and then we have the inputs,
which in this case is simply the image and the mask. And then we have the type of the tensor of the output tensors. In this case, it's float 32. So all we need to do here is just specify float 32, and then TF float 32, because we obviously have the input image and the mask. There we go. So at this point we have the output. Now what we're going to return here is going to be the output 0 and output 1. So this is the image and the mask. But because we are going to be using the Segformer method from Hugging Face, we have to know exactly the way or the form in which the Segformer method, or rather the Segformer model on Hugging Face receives its inputs. So based on this, we are going to be able to know exactly how we are going to generate our outputs. That's our dataset outputs. So in this case here, you see it takes in this pixel values, and take note of the shape: batch by number of channels, by height, by width. Now all this here are optional, and then we have the labels, where again we have the batch by height, by width. Now if you could remember, let's get back here. If you could remember, get back to the code. Okay, so as we're saying, if you could remember, back here we carry out the squeezing. Now the reason why we actually did this was because we do not want to work with 825 by 550 by 1, since this Segformer model takes in inputs of shape, height by width. So that's the reason why we had that. And so getting back here, we have our outputs, and then because we know that we have this dictionary that we need to pass in, what we could do is we could simply create a dictionary and then specify the name. So we have pixel values, as we had in the documentation. So pixel values, and then here we have labels. So we have pixel values and then the corresponding labels. So that's it. There we go. We have our dictionary. This should be instead the colon. There we go. Now also remember, as we've just seen in the documentation, it's batch by number of channels, by height, by width. But so far we've been outputting batch by height, by width, by number of channels. So we need to transpose this. That said, we simply make use of TensorFlow transpose. So we have transpose, and then here we are going to change this up. So we go from our initial, that's this, height by width by number of channels, to channels by height by width, by simply making use of the transpose method, as we've seen. Now if this is 0 and this is 1, then this is 2, and then this is 3, then here this is, let's give the space, this is 0, this is 1, this is 2, and this is 3. So here we are going to specify that we are going to have 2, 0, 1, and we'll explain why we have 2, 0, 1. So let's close this up here. There we go. Okay, so the reason why we're having 2, 0, 1 is because initially we have batch by height, by width, by number of channels, and since we want to change this into batch by number of channels, by height, by width, we want to make sure that this number of channels, or this height, goes from this position to this other position, that it goes from 1 to 2. Actually, this doesn't have to take into consideration the batch. So let's take off the batch and redo this again. So let's take off the batch, 0, 1, 2, 0, 1, 2, and then 0, 1, 2. Okay, let's take off the batch and redo it again. Okay, so as we're saying, this height goes from position 0 to position 1, and then width goes from position 1 to position 2, and the number of channels goes from position 2 to position 0. So what we have at the 0th position here is what we had previously in the at the second position. Maybe we should change this and put below, so that it makes more sense, because we're going from what's above to what's below. So we're going from this to this other one. Okay, so that's it. So as we're saying, we have height. Like previously, the on now what we have as channel was previously at position 2. What we have as height was previously at position 0. What we have as width was previously at position 1. So that's why you have 2, 0, 1, obeying that order. And then we have the same output or the same label. Then that's it. So we just simply create our validation augment method tool. So we have validation augment, val augment, and then we have here val argument instead. So that's val augment, that's val argument, and everything looks fine. Let's run this again, and then instead of this, instead of having this argument, now we have augment. So here we have augment, and then here we have val augment. There we go. So we take this off and we run that. Let's check out what we get in the outputs. Let's check out our data set. So for I in train data set, let's take a single value, print out I, and see what we get. You can see here we should have, okay, so we see we have our inputs. Scroll to the top, let's get back. Okay, so we have here batch, see, by number of channels, by height, by width, and then our values have been normalized. So that's it, which makes sense. Scrolling down again, you see now we have, let's get back here. Here we have our labels. Here we have a batch by 512 by 512. So that's it. So we have the image and the corresponding labels, and that looks fine. Now the batch is set to 32, so it makes sense that we have 32 different elements when we run this. We've just completed a section on pre-processing, and now we'll dive into data visualization. Getting back to the code, let's import Matplotlib. So import matplotlib pyplot as plt. There we go. And then we'll define, or we'll create this figure and specify its figure size. So we have fixed size, which will be 50 by 50. And then with this set, we would go ahead and plot out or visualize some elements in our validation data set. We'll start with the validation data set first, because since we have no data augmentation, we will have the images looking exactly like what we have in the data set. So we have for data in validation data set, let's take out a single element, and also note that the batch size is 2 for now. So we've set the batch size to 2, so we could visualize 2 samples from our data set, and then we'll simply take the image. So we have data, and then we specify the pixel values. Remember, we had created this dictionary made of pixel values and the labels, and then we also obtain the labels. Here we have data, and then we have the labels. There we go. Now what we want to do is to create subplots. Now the way we want the subplots to look like is simple. We would have our image here. Let's say our image is in blue, one image, and then we have another image like this in blue. And then we have the corresponding maps, or the mask rather. So we have the corresponding mask in red. So we want to place this side by side. There we go. We have the image and its corresponding mask. We just want to have 2 samples like this simply. So here we have the image, and then we have the mask, and then we'll have another image, and then its corresponding mask. And to build this, we'll make use of subplots. So we'll define a subplot which is made of just one row, that's this row, but 4 different columns. So it's going to be made of 1 row and 4 columns, 1, 2, 3, and 4 columns. With that said, for I in range 4, or better still, we could say batch size, because our batch size here is 2. Now batch size by 2, because obviously we have the image and its mask, so that's why we have batch size times 2. And if I gets to 4,
we just simply break. But in this case, it's not going to break. But if you have, if we change the batch size, then you can have this case, and we just want to have 2 samples, so we're gonna break out of the loop, and then now we create our subplot. So we have subplot, and then we specify 1 row and 4 columns. So we have batch size times 2, I plus 1. So we keep, there we go, let's take that off. So we keep incrementing I. That's it. If now, that's in the case where we want to plot the image, that's in this case where we want to plot the image, since we're going from 0 to, or it's actually I goes from 0 to 4, so it's actually 0, this is 0, this is 1, this is 2, and then this is 3 and not 4. So we have 0, 1, 2, 3. So whenever we plot images, we will notice that this value, that's 0 modulo 2, 0 mod 2 is equal 0. So 0 mod 2 is equal 0, and 2 mod 2 is equal 0, but 1 mod 2 is equal 1, and 3 mod 2 is equal 1. So we'll just test if the value of I modulo 2 is equal 0, then we know that we are printing out, or we are going to plot out the image. So let's get back to the code, and what we'll do here is if I modulo 2 is equal 0, that's if I modulo 2 is equal 0, then in this case we are going to be plotting out the image. So we have show images. So you see here we have images, and then we give it the title. So we'll title it the image, and then else, that's in the case where this modulo 0, that if this modulo 2, I modulo 2 is not equal 0, that's equal 1, then we would instead plot out the labels. So here we have show, and then we plot out the labels. So let's have the title, and then there we go, we have labels. That's it. So we also do plot axis off, so we don't want to have the axis shown, and then we end up with plot show. There we go. So that's it, and let's run this and see what we obtain. Now checking out the reason why we have this error, we see here invalid shape 2 by 3 by 512 by 512 for image data. So clearly we needed to specify the batch. So we have here I, and then here we have I. So let's run that again and then see what we get. Invalid shape for image data. Now with Matplotlib, the inputs needs to be H by W by C. That's height by width by number of channels, instead of number of channels by width by height by width. So again, as we had seen last time, given that we're going from 0, this is 0, this is 1, and then this is 2, and we want to end up at, this is 0, this is 1 here, and this is 2. So we want to go from this position below to this other position above. So now, given that we want to move from CHW to HWC, we are going to have 2. So this H previously was 1, so it's 1, and then the W previously was 2, so 2, and then the C previously was 0, so 0. Since we're going from this position to this position, we just have to look at what this different values were before, or they are put different positions before. So we have 1 to 0, and then we transpose. So again, here we're going to transpose our image. We have transpose, and then we specify 1 to 0. That's it. That looks fine. Let's run this again and see what we get. There's a bracket that was never closed. Let's close that up and run that again, and we should get our images plotted. We still have an error. This time around we have an image and its label, and then the next time we get in this error, slide through and see what we get. The error we get in is slice index 2 of dimension 0 is out of bounds,
And when we look at the code we have written here, it's clear that when I goes, let's say, to 2, then we'll be looking for images 2, and when I goes to 3, we'll be looking for images 3, whereas the batch size is just 2, and we want to, or we have only images, or we only have 2 options, that's 0 and 1. So one thing we could do is, let's print this out so you understand why we'll make this modification. If we print this out, you would find that dividing and taking the whole value and not the remainder ensures that 0 1 is still 0, and then 2 3 is still 1. So with this in mind, we would always have the first 2 samples simply. So let's just divide by 2, and then here we divide by 2. We run that, and then we should have our images and the masks printed correctly or outputted correctly. So there we go. We see we have the image and then its corresponding mask. Then here we have this image and also its corresponding mask. Now let's change this a little. Let's get to the train. Let's have the train. Run that again and see what we get. Could increase this so we could see that much clearer. There we go. Okay, so we see now that our inputs have changed or have been modified. As you can see, we have this image. You could also notice the shadow which we've added here. We also have the mask which matches up with the image. We have this image which has been rotated, and we also have the mask which matches up. So this is what we're going to train our models with. Now let's run this again. Because we have shuffling, normally we should have different images printed out so we could see other options. You see here, again, you have this rotated in this other direction, this rotated in this direction, and that's it. But you notice that the head is cut off in both cases. Anyways, you have an idea of the data you're dealing with. Another way in which we could visualize our data is by making use of a specialized tool like Voxel 51, and this takes us to our visualization part 2, where we are going to be making use of Voxel or the Voxel 51 platform. This platform permits us curate better data much easily by helping us visualize, as you could see here, our data in a very easy and intuitive manner. Also helping us, as we said already, curate this high quality data sets. You have public data sets or common data sets like the Cocoa, Open Images, and ActiveNet, which are already available. Thanks to this 51 tool, we could easily find mistakes, and this would help us train better models, as data quality is a key limiting factor on model performance. So the 51 tool permits you easily identify these mistakes. We also have this 51 brain, which helps you identify edge cases. You could check out this figure to the left where we have this visualization of embeddings, and as you may know, with embeddings or by visualizing embeddings in this way, we are able to get much more information about our data set, and this really plays a great role when curating data. Then finally, because we're able to curate and evaluate our data much faster, this leads to us or different teams getting into production even faster. So with this, we would dive into how we could make use of the 51 app to visualize our segmentation or semantic segmentation data. Diving back into the code, we'll start by installing 51 and then importing it. So import 51 as FO. That's it. So while this is installing, we'll get into the user guide. So we have this documentations right here, which you could feel free to check out. It's quite elaborate and contains a lot of stuff you would want to learn about the 51 app. So that said, we could dive into, first of all, you could check out the basics, and then dive into loading data sets. Let's get back to basics. Here we have the basics. Here you see how we have the key terms explained, like data sets. We have samples, we have fields, media types, tags, metadata, labels, dataset views, and aggregations.
Nonetheless, we're going to dive straight into loading the data sets. So we have loading data sets from disk, because we have our data set in our drive or in our Colab notebook which we've downloaded. So we could simply search for segmentation. You could see already that we have different types of data sets which we could load. We have object detection, we have image classification, we have even video data sets. So feel free to check that out. That's image segmentation. So there we go. And what we see here is the formatting of our data set. And it happens that the way our data set is formatted suits this FiftyOne's way of formatting. So here we have the data set directory. You have one directory for the data, that's for the images, and then we have another directory which contains the labels, exactly what we expect. Here we have file name 1 with the extension, file name 1 with the extension. So that's it. And then scrolling down, you see how to use this in Python or the command line. So given that we're working with Python, we could simply copy this out. So let's copy here, let's copy this, and then get back to our notebook. There we go, it's already installed. We have imported our 51, and then we paste it in our dataset directory. Let's paste it in here. We have dataset. Oops, let's get back. Paste that. We have dataset, and then we have you see we have 51 dataset from directory, and we specify dataset directory, which we've just done. Then the dataset type, you see, image segmentation directory, and then we have the name which we've already specified. So that looks fine. Now let's run this and see what we get. We are getting an error. Data directory content dataset data does not exist. Remember from the documentation we had seen, okay, from here we had seen that oh, let's get back up. We had seen that this, if we specify the dataset directory, then it's going to search for the data directory under labels directory. So given that that's not exactly the names we've used here, we are going to follow this second format. Here we have the data path and the labels path. So let's copy this instead. Data path, labels path, that should be fine. So we have, let's replace this dataset directory with data path and labels path. So we'll just go ahead and copy images. So let's copy that, copy path, and then paste in here, and we do the same for the labels. So that's it. We have taken off. This actually should be with images, so we should have images, and then we paste that in, and then we have masks. That should caps. Should have masks. Well, this is also PNG masks. Okay, that looks fine. So now we have data path. Let's get back a bit to check out the documentation. Here we have data path and labels path. So we'll just copy this out and paste. We have data path and labels path. Let's run this again and see what we obtain. We still have an error. Dataset name clothing dataset 1 is not available. Now the reason why we're getting this error is because the first time we try to create a dataset with this specific name, and so this has already been stored in the database, so we could only load this dataset at this point. So that said, we should change this to 2, run that again, and we should now be able to get some outputs. Here we get another error, but you could see already that it started loading. So 1 out of 923 elements or samples started loading. We are getting this next error because the way we named our masks was different from the way we named the images. You could see here we have this key error seg, and its number is 0001. So what we have to do now is rename our masks such that they are all IMG instead of seg. Now to rename this, we also have to take into consideration the fact that right from the beginning we took this to be seg. So instead of this, we would have IMG, and then here we would have IMG, and then IMG, and then IMG. Okay, so that's what we're gonna have now instead of seg. Let's go ahead and rename this. So that should be before, or let's just put it in here. So we're gonna import OS, but this looks like it's already been imported, so we don't need to import this. Okay, so we have that, and then now what we want to do is rename each and every file we have in here. Now we have our image path, in path, and annotation path. At this point, we're supposing that we are yet to split. That is, we are yet to move these files. So we'll just work on the original folders. That said, what we want to do at this point is take in the initial path, and then we want to have the renamed path or renamed file. So initial file path, and then we have the initial file path, and then we have now the renamed file path. And then we are going to go through all these different images. So for for image in the list, let's take the list of all images in path. For this list, we are going to do the renaming. Now this image here is going to be the file name, so let's print it out so you could see that clearly. Print the image, then break out of this loop. There we go. Let's take this off and print that out. So once that's printed, we see we have the file name right here. So what we want to do now is take rename, and then take the image path, plus this image, or plus this file name, or let's just call this file name. So plus the file name, we want to have the file name, and then let's make it shorter, file name. So there we go, we have file name, fname. Okay, so we have the file name, and then we add this to the image path, and then once we add this to the image path, we have this initial file path. Now for the final or the renamed file path, we want to have the same image path, but plus this time around image, and then we have the image, and then plus the file name, but starting from the underscore. So we have 0, 1, 2, 3, starting from 3. So we want to have fname starting from 3. That's it. Now you should note that we don't need to do this for the images because they already have img. We just need to do this for the annotation. So take this off and do annotation. Okay, so that's it. So this should work fine. Let's run this and see what we obtain. Then we just refresh. No such file or directory. The reason why we're getting this error is because this was supposed to be annotation path and not the image path. So we have annotation, run that again, and all our files now should be modified, or their names should be modified. So if we open up masks, you should see that still have sex. Let's get back and refresh. Then data set, png masks, open up masks, and normally they should be fine because we didn't run into any error when running this here. Okay, so that's fine. So now we've renamed our files. Now what we'll do is that we are just going to disconnect and then restart, so that we make sure that both the training and validation sets now have this new file names. We've restarted the notebook and running this cell now. We should get our data set loaded. We still have this problem. Say 2, run that again, and then they should be fine. You see, we have our 923 different samples, and we have the sample fields described. First of all, we have the name, we have the media type, image, number of samples, whether the data is persistent or not, tags, no tags, sample fields, ID, file path, tags, metadata, ground truth. Now for this specific sample, or picking one sample, we could find that it has its ID. So 51 gives the sample, each sample an ID. The media type is specified, the file path, so in this case is this image, and then no tag, no metadata, then the ground truth. Now this ground truth here is simply our label, because we have the input, that's the image, and then we have the label. Now it's segmentation label, so that's why this is specified, and then we have the ID, then we have the mask path. So here we have the image path, and here we have the mask path. So this is what we obtain when we print out the data set. That's a summary. And when we print out the data set head, that's a few samples from our data set. Now at this point, we could go ahead and launch the app. So we could do session FiftyOne launch app, and then we specify simply data set. We now have our app launched. Don't forget to give the project a star on GitHub, and also join the FiftyOne Slack community to meet other FiftyOne users and computer vision enthusiasts. Okay, so that's it. So you see, it takes a little while, and then comes up. So there we go. You could see already this interface. Let's reduce so you could see this much clearer. There we go. Okay, so we have this interface. Well, it's taking a little bit too much time. Let me refresh this. Let me run this again, and it should be coming up soon. This now shows up, and you could see at the top here, clothing dataset 1. You could select another dataset in case we had created another dataset. Then we have the filters. We have the metadata, which you could open up. Like you could see this width, metadata width. They see there's no result, there's no height yet, but we could actually put in this information. Then looking at the labels, we have the ground truth, and we have ID, max path, tags, and then we have primitives, that's ID and file path. Looking to the right, we can see our annotated images, and instead of getting to open up or view images like this in some folder and then having to get back and check out the masks like this, for example, you have these two combined together for each and every image, and also colored for per class. So each class has a specific color. Now, if you to open any one of these, you just need to click on it, and this one loads up. Once it's loaded, you could have here the primitives, that's the ID and the file path. Then you could also check out the metadata in case you have given FiftyOne this information. So hovering on the image, like we start from those lenses, you see, you could read out there clearly 47. That's to tell us that the sunglasses have ID 47 in our labels. And then you have the max path and the ID. So as you change this, you see it goes now to 55. Next, you could check out shoes, for example, 39, socks, 45, and that's it. You could check out hair, 19. You could check out this pullover, 5, and you could check out skin, that's 41. Now let's get out of this view. We could pick another person. Let's pick a male. Here we have something similar to what we had already. Here again, we have those different labels from hair, skin, shirt, coat, trouser, shoe, or maybe socks. So that's it. Now you could take out the ground truth by simply clicking on this. So once I click on ground truth, I have the original image. And when I click back at the ground truth, see I have now the original image with its mask. We could also swipe and move to the next image. So we load the next image. Here you have the color settings. Click on this, you have color settings. I could modify this opacity of the labels. So let's reduce this opacity. And then we have save as default. You see that reducing the opacity makes it look much more transparent. Let's increase that. And then save as default, and you see that it kind of now covers the image. So depending on how you want to view your data set, you could modify that opacity. Now let's get back here. We'll start by filtering by mask path. We'll skip the filter by ID and dive straight into filter by mask path. So depending on the path you want to filter the image. So let's say we have 0001. Let's see, you see it filters that image, and we have this image 001. You could see by opening up this image here that this is exactly what we expect. So this is the image 0001. This is this image with the size, the type, file size, and the folder given. Then when we get back here, you could see that exact same image. So you could simply, or if you want to see a specific image, you could simply filter. So let's say 00 or 0099, 0099, no results. Most probably this has been sent to the validation data set, so that's why we're not seeing that. Well, we made an error and instead searched in this ID. So let's check that out. Instead, in the mask, so we have 0099 in the mask path. We should obtain that specific image, and there we go. We obtain our image. So this is that 0099 .png file. Now another interesting thing you could do is actually to search again for another. Let's say 6. You see, now we have this, we have selected this 2, so our view right here will be made of only these 2 images. So you may have some specific criteria, or based on some criteria you want to filter some parts of the data set so that you can just view only those. And the FiftyOne app makes it very easy to carry out this kinds of filtering and visualizations. Then from here, another thing you could do is simply save this view. So if you're interested in only these 2 images, then you could save that view. So let me say save current filters as view. So your view name, we'll call it 099 1000. So 0099. Okay, just some random images. There we go. Color, let's maintain that gray, and then we save the view. So that's it. So we have our views now saved. We should get back to the original view. That's without having to filter. So let's take this off, or let's reset this. Actually, resetting this, we take all this off. So now we have the original view with our 923 samples. And then each time we want to view this, you see, each time I want to view this, I just need to click, and there we go. Just click on that, and my 2 images show up. That's it for this section on data preparation. In the next section, we'll dive into modeling and training with a Segformer model, which is available on Hugging Face. After preparing the data, the next step will be to dive into modeling. First things first, we shall start by explaining the Segformer model which we are going to use, and then we will dive into model creation with TensorFlow. The Segformer model was first developed in this paper entitled Simple and Efficient Design for Semantic Segmentation with Transformers. That was in 2021. And this model, which you could see right here, essentially it's made of 2 parts. That's the encoder section and the decoder section. Now, talking about the encoder and decoder sections, we could get back to 2015, that's 6 years before the Segformer paper, where the UNet paper was published. The UNet architecture itself is made of the encoder and the decoder block. So here on the left of the U, you have this encoder block. Let's make that transparent so you can see that. We have this encoder block. And then to the right, we have the decoder block. Let's change the color. There we go. Okay, so we have this encoder and then the decoder blocks, which make up our UNet architecture. Now, unlike with image classification, where our output will be some vector, and in which each position in that vector will be a specific class which we will expect our model to pick from all the remaining classes. Here we have an output which is similar to the input. That is, we're going from an input image of shape height by width by 3 here represents the number of channels, to an output of shape height by width by 1, or sometimes we could just consider this to be height by width. So the important point to note here is the fact that the kind of output in the case of semantic segmentation is different from that of image classification, and hence a UNet architecture makes a lot more sense here. It should also be noted that in practice, this is
generally h divided by 4 and width divided by 4, because it's much more computationally expensive to have to generate or reproduce this output with the exact same dimensions as the input. So here we have h on 4, width divided by 4. So this figure will look somewhat like this instead. So we have this input and then this output. Getting back to our unit architecture, in this blocks we have right here, we have the usual convnet layers, and then we have the downsampling by the max pool layers. We have here max pool. So essentially we are making use of convnets and max pool to downsample the inputs. And then in the other turn, as there's a downward turn and this upward turn, we have again the convnet layers and the upsampling layers. Then in between this downward and upward turns, we crop out parts of our features in these blocks. You could notice that, or you could take note of that with the dotted lines. And then we concatenate this to the blocks in the upward turn. We suppose that you already have an idea of how the conv layers work, but let's take this simple example which will show how a simple conv layer works, and also how the upsample layer, which is the conv2D transpose layer, works, which can be used for the upsampling. So let's suppose we have this example. Then in this case, if this is a kernel, so let's say this is a kernel and then this is an input feature. In this case too, we have an input feature, and then here we have the kernel. So we will take this input kernel and multiply by this part of our input. So this is 2 by 2. Here's 2 by 2. We take 2 times 0, 4 times 0, all of that 0. Then 1 times 1 plus 1, 6 times 6. That's 36 plus 1. So we have 37. So at this point we have 37. And then we are going to take this off. We're going to take this off, or we're going to just shift this. We shift this. You see, we now multiply 4 times 0 plus 6 times 0, that's 0. 6 times 1, that's 6, plus 4 times 6, that's 24. So 6 plus 24, 30. We have 30. We just have here 30. And then for the next, we'll just move this again. So let's move that. Move this. And then we multiply again. We have 0 times 1 plus 0 times 6, that's still 0. And then 1 times 1, that's 1, plus 6 times 6, that's 37. So again, here we're going to have 37. So you see the output we are obtaining. And then we'll shift this again and multiply 6. This is 6 times 0 plus 4 times 0 plus 6 times 1 plus 4 times 6. So that's 30. So again, here we have 30. So that's fine. So now we have this output, and there we go. So that's how the conv layer works. For the conv transpose layer, which could be used for upsampling, it works slightly different way. So again, we have this kernel, then we have this patch or this part. We take 5 times 0 plus 5 times 0. We select this patch and multiply by all those different values here. That's for all these different positions. And now we have this 0. Here we have 0. 5 times 1 is 5. There we go. 0 times 6, or rather 5 times 6 is 30. So that's what we obtain. And then we'll move this patch again, or we'll move this position again. So we go to this. Here we have 2. There we go. We have now 2 times 0. But note that we are not going to do 2 times 0, 2 times 0, then put it out this way. We're not going to have 2 times 0 like this, 2 times 1, and then 2 times 6 this way. What we're going to have instead is we're going to have these frontier values, which are going to be added to these other frontier values. So it's going to be a combination of those values. So let's have this way. You see it's going to be something like this. So this is superposed. Let's just put it out this way. Okay, so that's how it's going to look like. And then for the next, let's shift this position to this next one. We have 1 times 0. Let's write that out. We have, let's change the color so you could see that clearly. Take green, and there we go. So we have 1 times 0, 0. Again, we have 0, 0. So we'll have 0, 0. See, we're adding that 0 again. And then 1 times 1 is 1. And then 1 times 6 is, or rather, yeah, 1 times 6 is 6. So we have 6. And then for this last position, we will take this and move to 0. Well, for 0, obviously, all values will be 0. So we'll just pick another color. Let's pick, say, black. Let's pick black. And then there we go. We would have, take that black. There we go. We have 0. Here we have 0. Here we have 0. And then here we have 0. Okay. So now this is this final result. Then from here, we could, let's drag this up so you could see clearer. From here, we just have this output matrix, which is going to be, let's take this pen. Our output matrix now is going to be 0. So here we have 0, we have 0, we have 0, we have 5 plus 0, that's 5. And then we have 30 plus 1 plus 0 plus 0, that's 31. Then we have 12 plus 0, that's 12. Then we have 1, then we have 6, then we have 0. So that's it. And so now we see clearly how we are able to leave from an input which is 2 by 2 to an output which is 3 by 3. So that's a simple upsampler. At this point, we're still in 2015 with a UNet model. Now we move to 2021 with our Segformer model. And with the Segformer model, we'll still use the encoder and decoder as we've seen already. But now, instead of our blocks made of conv layers, we have the transformers. The Segformer architecture came with 5 major methods, which made it the state-of-the-art in semantic segmentation back in 2021. The very first of this is the hierarchical feature representation. Now, as we had seen with the UNet, we already had this hierarchical representation. But then with the VITs, that's the vision transformer, this is the transformer which precedes other transformers like the Segformer, we didn't have this hierarchical structure. And so what the Segformer did was borrow this hierarchical structure from other models like the UNet. The reason why the authors decided to work with this hierarchical structure is because when we represent features hierarchically, at higher resolutions, we obtain or we are able to extract more coarse features as compared to the lower resolutions where we tend to extract more the finer features. And so with this, we mimic the kind of feature extraction mechanism we had already with the convolutional neural networks. Now that said, let's take this off and see how in practice the patch merging is done. Now it should be noted that with the VITs, shift this, with the VITs, if you have an input like this one where you have 8 pixels by 8, you could count them. We actually have in 1, 2, 3, 4, 5, 6, 7, 8 pixels by 8 pixels. Now for the input, let's get to the VIT paper. Here's a VIT paper. As you can see, we have in this case it was actually 16 by 16. So what we did here was we flattened these patches, and here if we have VIT, then we would simply take this one and then this next one. Let's instead do it this way, so it's simpler. So we take like this and we flatten it out. Let's pull this way, copy this other one, let's cut that and paste. There we go, right up to where we have all this flattened out. And so at the end, we are obtaining this output feature, which is 1 by 1, because obviously here you have 1 by 1, but it has a certain number of channels. In this case, since we have 64 pixels, then we will have 64 channels. But if this input was 8 by 8 by 3, that is if we had 3 channels, then the output will be 1 by 1 by 64 times 3. Either way, you understand that this is how with the VIT we're able to flatten out the patches. Now we're going to do something similar with the Segformer, where we are going to regroup these different pixels together. So let's take this off, or let's just put it up here so you see that clearly. 8 by 8 by 1 to 1 by 1 by 64 times 3. Now as we're saying, we want to go from, as you see in the paper, we have the original height by width by, let's say, 3, and now we want to obtain height divided by 4 by width divided by 4 by channel, let's say C1. So getting back here, given that we have 8 by 8, it means that we are going to obtain 2 by 2, because 8 divided by 4 is 2. Now obviously in practice, it's not actually 8 by 8, like the inputs would generally be, let's say, 512 by 512, and so it makes sense that you could go up to, let's say, height by 22 by 32, width by 32. So getting back here, our output is going to be 2 by 2. So we'll make sure that this part, let's take off this 8 from here. We'll make sure that this part, this quarter, you see, let's copy that quarter. We put it out here. Then we flatten this out. So again, just like with this, we just simply flatten this out. So this first quarter, we flatten that out. Let's break this up with a pen so you see that clearly. So we have this like that. There we go. So this first part, we take it here and then we flatten it out. Then once we flatten out like this, we move to this next quarter. We take all this and then flatten out again. So what we just do is simply just copy this and paste. Okay, so let's copy that and paste. Maybe we should change the color so it looks different. There we go. Let's copy this color code. So we just recolor this part here. Okay, so paste it out and there we go. Okay, so that's fine. And then this other zone, for this other zone, we have, let's pick that, let's pick this red, let's pick yellow. Okay, so we pick that, copy the color code, and then we're going to do the same with this. So paste out. You can see this top left quarter, here is it in blue. Then this top right quarter, here is it in orange. We have this other quarter yellow and this other quarter green. If we join this together, this should be below, so let's put this around about this. Make it this way. Okay, that's fine. So you see, if we bring all this together, now you have this output, which is 2. See, because here you have 2 pixels by 2. So this is it. We have 2 by 2, and then we have a certain number of channels, and that's exactly the way the authors did to downsample the inputs or the input features. The next method, which was implemented in the Segformer paper, was the overlapped patch merging. Now with the overlap patch merging, it's simply the same as the patch merging which we've just seen, but with the difference that this time around it's overlapped. So unlike what we just seen, which is actually non-overlapping, with the overlapped patch merging, we'll do something a little bit different. So before we took this quarter, we took this quarter, this next quarter, this quarter, and this other quarter, and then we produce this output. Now instead, what we'll do is we are going to overlap, that is, get into the other quarters while trying to produce this output. So this overlap now. So we'll make use of all this part to produce the first this first part of our output, and then for the next we'll just shift this. So let's shift this to 2. We'll move this way. See, it takes in part of this quadrant, this quadrant, this quadrant, and this quadrant, and this ensures that we have local continuity between the different patches, unlike with the non-overlapping patch merging. So for the next one, we just simply drag, we pull this, there we go. Let's pull it this way. So you see, for this other part, we just do this, and then for this other part, that's the bottom left. for the bottom left, we'll simply do it this way. Okay, so that's it. So that's the overlapping patch merging. And then we'll move to the next, where we have the efficient self-attention. The efficient self-attention, as the name goes, provides a more efficient way of carrying out the self-attention. Now the self-attention, as from the original attention is all you need paper, this is the transformer paper, can be shown with this formula. So essentially, the computational cost of this operation cure by KT is big O of n squared. And the reason why we have big O of n squared is simply because if cure, that's our query, is given to be an n by e matrix, and then we have k, which is also an n by e matrix, then multiplying this by k would be multiplying this by an e by n matrix, and so you end up with an n by n matrix. This means that if you have a very large value for n, then you would end up with a very large matrix, which is also very expensive to compute. Now that said, in the domain of computer vision, values of n are pretty large. So n in our case will be height by width, so it will be h times w. So if you have a height of, let's say, 512 and a width of 512, then you'll be having 512 times 512, which is pretty large. And so the role of this efficient self-attention method is to see how to compute this cure KT much more efficiently. So let's take this off and show you how this actually is done. So what we'll have here is we're going to take this h times w and divide by a factor r. So if it's divided by r, then let's just copy it and put, let's take this from here, copy it and put this way. We have h times w divided by r, and then the c will be multiplied by r, so we will be able to reshape it. Now note that if you try to if you just divide this by r and maintain c, you cannot reshape. So that's why you need to divide by r and then multiply by r, so you will be able to reshape. Now that said, what this means is you're going to have this side reduced, because now this is the h times w divided by r. Let's divide it here. We have divided by r, so this side is going to be reduced. See, it's going to be reduced, divided by r, and then this other side is going to be increased because now you've multiplied by c. So let's multiply here by c by r, sorry. So we multiply by r, and that's increased. Now from this point, what next we're going to do is we are going to simply project this to c. So with a linear layer, we can obtain c from c times r. So just like in the paper, see here, you have in the paper, there we go, we have this linear projection which takes c times r and projects it to c. So just like as in the paper, we're gonna get back to our original shape in this other direction. So now we're gonna have c instead of c by r. Let's actually come and measure it here, so you see it's actually exactly c. So you see that's c, but the h times w divided by r still maintains. So we can just copy this from here and then paste out here. We have h times w divided by r, and then we have now c here. So you see we have left from h times w by c to h times w divided by r by c. And now instead of multiplying, so this here had h times w, let's call this n. This was n by c. So instead of multiplying n by c with n by c transpose, now you're going to multiply n divided by r by c times n by c transpose. And so we go from big O of n square in complexity to big O of n square divided by r, as we have in the paper. So here's in the paper, we go from on squared to on squared divided by r. And this is very important because as we've said already, in computer vision, the value of n is generally very large because we're dealing with high values for the height and the width. And then they said r to 64, 16, 4, and 1 from stage 1 to 4. So depending on the stage, let's increase this. Depending on the stage, you would have different values for r. Copy and paste. Okay, so depending on the stage, you have different values for r. And so this makes the self-attention much more efficient. There we go. So that's it. So at this point now, we'll move on to the next method, which is the mix feed forward network, mix FFN. In the vid paper, the positional information or information about the position is added on to the linear projection of the flattened patches. So here we have patch plus positional embedding. You could see that. You see here, for example, 0, 1 to up to 9 to give us a position, or to tell us or give us information about the position of each and every patch. It turns out that this way of getting information about position works fine when we have fixed inputs. But when we are in test mode and that the inputs we are getting are different from, or the shape of the input is different from the shape of that which we use when we're training, then this way of storing or locating each and every patch doesn't work so well. And so what the authors of the Segformer paper did was they simply encode positional information using this 3x3 convolutional layer. So that said, we've treated all the different blocks which make up our encoder. We can now look at the decoder path. Now essentially, we have a lightweight all MLP decoder. And the reason why we need just a lightweight all MLP decoder without any transformers is because of the hierarchical architecture we have at the level of the encoder, which permits us have an effective receptive field. Below in this figure, you could see the receptive fields of the DeepLab version 3 Plus and the Segformers compared. We could see how even at stage 4, the receptive field of this DeepLab version 3 Plus is still pretty small compared to those of the Segformer at the different stages. And this is simply because of the hierarchical structure or architecture at the level of the encoder. And because we have this features rich information passed into the decoder, we do not need to have a very complex decoder architecture. So at the level of the decoder, we just have this lightweight all MLP decoder because the encoder has already done a lot of work when it comes to extracting the codes and the fine features from the inputs. And that said, you could see how with fewer parameters, the Segformer models outperform the other models as of 2021. Now we understand in detail how the Segformer model was built. We are going to go ahead and create a simple Segformer model with Hugging Face. We shall head over to the documentation where we have this Segformer docs. Then we click on the TensorFlow Segformer for semantic segmentation. And once you click here, just simply go ahead and copy out this part where we create the model from a pre-trained one. So let's copy this out and then paste in here. There we go. Now it should be noted that this model ID is for the Segformer B0, and as we have seen in the paper, Segformer comes in different variations. That's from B0 right up to B5. So getting back to the code, let's copy this out. Let's take that off. Let's just call this model ID. There we go. So that's our model ID, and we'll define model ID just right up here. Model ID is equal this model ID, and as we've said already, this is the B0, so we could change it to B5, and then it's trained on the ADE 20K dataset. Now other parameters which we're going to pass in here will be the number of levels. So we'll have number of levels which we're going to define num levels, and then we'll also define ID to levels. So ID to label, ID to label, and then we'll also define label to ID, and then label to ID. There we go. Finally, we do ignore mismatched sizes. Set that to true. Now to obtain this ID to label, label to ID, and number of labels, we'll make use of this labels.csv file. So we could open that up and check it out. Let's open this up. You see, this is our labels CSV file. Now let's copy the path. We'll just copy the path, and then we'll make use of pandas to read the CSV. So we have our data frame, pandas read CSV, and then we pass in that file path. So now we read that. Let's create another cell just below this. There we go. We create this other cell, and then we create our ID to label dictionary. Oops, we have this empty dictionary, and then we go through the data frame. So we have for ij in iterate rows. There we go. Oops, let's get back. We are going to say if I is equal to 0, then in that case, ID to label I is going to be equal none. So none. There we go. Else, ID to label I is going to be equal j label list. So we're getting this from here. So we have this label list. And this permits us now to get the exact label. So we're going from the IDs to the labels. So we're matching them up. That's it. So now that we have this set, this set, we could just run this and then print out our ID to label and see what we get. Let's run this and then say we have ID to label. Let's see what we obtain. See, we start from 0 right up to 59. Scroll. Okay, so we actually have 59 of them, so it goes from 0 to 58. So that's it. So we have now our ID to label, and then we could obtain from here label to ID. So let's just create this cell, and then the way we obtain label to ID is simple. So label to ID, we create a dictionary, and then we match the labels with the ID. So it's kind of reverse of what we had for the ID to label. So for ID label in ID to label items, we go through each and every item. Items, there we go. Okay, so that's it. So for every item we have here, we're just going to reverse. So ID becomes or ID takes the place, or label takes the place of ID, and ID takes the place of label. So let's run this again and then print out label to ID. Oops, label to ID. There we go. So running that, we could now see how we obtain. Scroll down, we see how we obtain our label to ID. So that's it. We've defined our label to ID and ID to label. You see, we could obtain this length by doing length of label to ID, and we should obtain the length. So here we just simply have length of label to ID, or length of ID to label. Take this off, and that's fine. So now we could run this and then create our model. And obviously, after creating a model, you could simply do a summary. We are getting an error, and what this error says is this model ID we specified is not a local folder, and it's not a valid model identifier listed on Hugging Face. So what we'll do is we'll get back to the documentation. There we go. We get back here and search for Segformer, and you'll find that that specific model isn't in that exact image size. So it's 640 by 640 instead. So let's get back here and modify this and have 640 by 640. There we go. So let's run again, and hopefully this time around everything should work fine. Let's take this off. Run that again. So as we're saying, we could obviously do a model summary. So we could have model summary, and we could also test this out. So we could take in an input of shape batch by number of channels, by height, by width, and then see what it produces in the output. Let's run this and see what we get.
Right here, as you can see, we have our model summary. It's a 84 million parameter model, and we also get the shape of our output. So because we have 59 classes, this makes sense. And then also we are having 128 by 128. So we're leaving from an input of 512 by 512 to an output of 128 by 128, which makes sense because we are living from height by width to height divided by 4 by width divided by 4. So this makes sense that we have this kind of output. And so that's it for the section. We'll now move on to the next section where we'll go ahead and train and then evaluate our model. We'll start with the training and evaluation, where we'll first of all create the optimizer. So right here we pass in the initial learning rate, number of training steps, which depends on the length of our training data and the number of epochs. Then we have the weight decay rate specified and the number of warm-ups set to 0. So let's run this, and then we compile our model. Once our model is compiled, we can start with the training. But before starting with the training, we'll create a callback for our model evaluation. So every time after every epoch, we want to take in our validation data and compute the mean IOU of the model. To understand how the mean IOU score is computed, let's consider the following example. Now note that mean IOU stands for the mean intersection over union. So if you have two examples, let's just draw this before we get to our main example. If we have these two boxes, then the red, and then we have another one. Let's change the color to blue so you could see that clearly. Okay, so if you have these two boxes, then the intersection of a union of them is simply going to be this area. That's the intersection. Let's change the color. This area right here, which is the intersection of the two, you see, then divided by their union. Their union is obviously all this part, this zone. Let me change the color again so you can see that clearly. There we go, we have green. Okay, so we take, as we're saying, we take all this here. This is their union. So all this is their union. So we take this part in white divided by all this to get the IOU. Let's consider that here we have the target output. So we expect our model to produce exactly this output. Here we have two different classes, or two different objects, we could say. So let's call this object A, and then let's call this object B, this object right here. The rest is simply the background. So this grayish zone here is the background. So we have object A, object B. Then we have a model, which we'll call model 1. Then we'll call this model 2. And then we'll call this model 3. So this model 1 predicts this output. And then the model 2 predicts this, and model 3 predicts this. Now, before getting to the IOU, let's suppose that we're using a metric like the accuracy. Now, if we're using accuracy, then clearly this here, this model 1 should have the best score. And that will simply be because we are going to go pixel by pixel and compare the actual with what the model predicts. It should be noted that whatever the model predicts here for this object A is in this yellow, and then for the object B is black. So this is what the model predicts. This is what the model predicts. This is what was expected, and this is what's expected. Well, this was what's expected here is in the back, is behind this. So that's it. Let's get back. Take that off. Okay. So as we're saying, with the accuracy, we'll go pixel by pixel and say, okay, for this pixel, what does the model predict? In this case, it predicts the background, and what was expected was background, so that's fine. We'll do that for all the remaining pixels. And so given that the model does a great job at predicting object A, although it makes some slight error here, so it's only this portion where we're going to have an issue with the accuracy. And then for this object B, the model doesn't even predict it, or doesn't notice that. So we also have this zone. So you find that these are the two zones where we're going to have issues, or maybe this thin line here and this thin line. Apart from this, we do not have any other issues. All the rest are correctly predicted, so our accuracy is going to be pretty high compared to these two others, where we have, you see, for this here we have this zone which is wrongly predicted, this zone wrongly predicted, also this zone, you see, wrongly predicted, this zone wrongly predicted, and then here we have this zone 2 wrongly predicted. So that's it. You see that this has the smallest as of all this. For this two, you see, we're gonna have this zone which is wrongly predicted, because this ought to be seen by the model as object A, but it is not seen as object A. So if you're using accuracy, then you consider that all these zones are not predicted properly, and hence this model wins, model 1 wins. But the problem now is, if you have or if you suppose that this model 1 is the best performant model, then you would end up with a model which doesn't know how to properly segment object B. And in a case where object A and B are of equal importance, then this is a poorly performing model, because it doesn't know how to predict or how to segment one of the major classes. On the other hand, the accuracy for model 2 will be the lowest, whereas it tries to segment at least both classes, that's class A and class B, compared to this model 1, which doesn't segment class B. And so with the mean IOU, we are simply going to compute the IOU for each and every object and then calculate the average over all the different classes. So in this example, we'll first start by computing this area, that is this intersection. The intersection is this here. So here's our intersection. We could change this to red so it's clearer. So as we're saying, here we have this intersection. You see, there we go. We have the intersection, and then we have the area, the union. Here's the union. We compute that. See, compute that this intersection divided by the union, and then we do the same for this. Let's try to zoom in so you could see that. So again, here we'll take this intersection and then divided by the union. It's clear that in this case it does very well with the class B, and so here we're gonna have a high IOU score. But nonetheless, with this class A, we're gonna have a smaller IOU score, but it's gonna be pretty reasonable. So we could get, say, 0.55. So here we get 0.55 for this with the IOU, and then here we get, say, 0.85. Whereas for this example, 0.85. Whereas for this example, we get, say, 0.9, and then here we have 0. So if you sum this up and then you divide, let's just get for this. For this, we can estimate that we get an IOU, because here the intersection is simply this part, this intersection, and then the union obviously is all this. See, all of that. So here we could get, say, 0.3, and then here we could get, say, let's say 0.9. Okay, so 0.3, 0.9, 1.2, we have an average of 0.6. That's for the mean IOU. And then here 0.90 divided by 2, we have an average of 0.45. So you see that the so-called best performing model, when in terms of accuracy, turns out to be the worst performing model with the mean IOU. Then here we have 0.55 plus 0.85, that's essentially 0.9 plus 0.5, that's 1.4, divided by 2, we have 0.7. So this turns out to be our best performing model as compared to the accuracy, which instead saw this to be the best performing model. And this makes more sense because all our different classes are of equal importance. And so the fact that we did well in predicting the larger object, we shouldn't rush to think that this is the best performing model, because the classes which appear smaller to matter. That said, dive into the code. We're going to import evaluate, and then we are going to have mean IOU evaluate.load the mean IOU. So let's run that. See, we now have our mean IOU loaded very easily thanks to Hugging Face. Let's define our compute metrics method. So here we have compute metrics, and what this metrics takes in is simply our predictions and the target output. So we have logits. This is what the model produces, and then the labels are what we expect the model to produce. So that's it. And then once we have this, the logits will be slightly modified. If you can see from here, you'll notice that we have batch by number of classes by 128 by 128. But what the mean IOU will need will be an output of type 1 by 128 by 128 by 59 instead. And so that said, we are going from batch by number of classes by height by width to batch by height by width by number of classes. So that's why we're going to permutate this. So we'll go from 0. Now this 2, 3. So you see 2, 3. So we now have 2, 2, 3, and then 1. So that's why we'll take in this logits and then permutate them or transpose. So we have logits, TensorFlow transpose, and then we're taking the logits and then permutate, and we'll specify it's going to be 0, 2, 3, 1, 2, 3, 1. Okay, so that's it. So now we have this logits. We're going to resize them because remember, the output or the target output isn't 128 by 128. Our target output is 512 by 512. So because we have this staggered output and not what this model produces, we will have to upsample this, and so that's why we're going to use a simple the resize method. So we have our logits, which is now resized, and then we'll make use of TensorFlow's resize method. Resize, there we go. We take in the logits on resized, and then we specify the size, the output size. So it's simply going to be the shape of the labels, because the labels are already having the shape 512 by 512. But because we do not want to include the batch, we're going to take 1, and that's it. Okay, so there we go. We specify the method. Want to have we make use of the bilinear interpolation method for resizing. Now, talking about bilinear interpolation is simply like this, as you can see from this paper by Sanjar Kashiev. Here you have an input, let's say 10, 20, 30, 40. Then if you want to go from 2 by 2 to 4 by 4, you see, take this 10, place here, 20, place here, 30, place here, 40, place here. And then to go from 10 to 20, we simply look for numbers such that the distance or the difference between all the numbers are the same. So 10 plus 3.3, 13.3, plus 3.3, 16.6, plus 3.3, 20. And then we do the same in this direction, the same in this direction, the same in this direction, and so on and so forth. So that's how we go from this 2 by 2 to a 4 by 4 by bilinear interpolation. So getting back to the code, we're going to modify this again. This is our logits or our predictions again. Here we'll define prediction print labels, and then here we have argmax and text and logits resized. Okay, and then we'll specify the axis to be the last axis, so -1. Now the reason why we're doing this is also because we do not want 512 by 512 by 59. We actually want 512 by 512, and so we use the argmax function such that for each and every position in this output, we are going to know exactly which class had the highest probability. So that's it. We have now our predictions, and then we could go ahead and compute the mean IOU. So let's just say metrics, metric compute, and then remember this is not actually metric. Here's going to be mean IOU, mean IOU. Okay, so we have our mean IOU compute, and then here we specify the predictions. There we go. We have pred labels, which we've just defined. We have the references,
references, we have labels. Obviously, from our data set, we have the number of labels, and then we have the ignore index in the index, which is set to -1. Okay, so that's it. Now, once we are able to compute our metrics, the next thing we want to do is to obtain the per category IOU and the per category accuracy. So here you take this metrics, we get the per category accuracy, convert to a list, get that of the IOU and convert to a list. Now let's just change this name to metric actually, because even though we load the mean IOU, we could also get a metric like the accuracy. So let's change this to metric. Okay, so that's fine. Now that we have our per category accuracy and that of the IOU, we are going to now update our metrics with the accuracy and IOU of each class, now specifying here using ID to label the specific class name. And then we'll return the validation metrics, which is going to be printed out. With the metrics method defined, we can now go ahead and define our metric callback. So let's create this new cell, and then we import Keras metric callback from transformers. Keras callbacks. Let's import the Keras metric callback. Okay, then we have our metric callback, which is simply gonna be metric callback. There we go, which is simply gonna be our Keras metric callback, which we've just imported. And then in here we're gonna define the metric function. We just created this metric function, which is compute metrics. And then the evaluation data set is gonna be our validation data set. We also specify the batch size, which is the batch size we've already set. So we have batch size. Well, it's actually 2. This is batch size we've set right here. So we could instead put this just below. So we just make use of this batch size, which has already been set. So let's paste it out here. There we go. We have this pasted out, and then we specify our batch size, which is set to 2. And then finally we have the label columns, which is simply specified as labels. That's it. So that's it. We've created our metric callback. We now define this callbacks list, which is going to take in our metric callback. So this means that you could specify all our callbacks and add them to this list. With our callback created, we'll go ahead and recompile our model and then start with the training. After training for several epochs, here are the results we obtain. As you could see, at the 15th epoch, we get in this loss of 0.28, validation loss of 0.36. The validation mean IOU is quite low, that's 0.18. And then the validation mean accuracy is also very low, 0.278. Then the validation overall accuracy is higher compared to the mean accuracy and the mean IOU. Now, it should be noted that the reason why our mean values are very low is simply because we have so many classes which aren't represented in our data set. So if you look at accessories, you find that there's very low value for the validation accuracy. Let's get to the IOUs. After the accuracies, you have the IOUs for each and every class. So we have more than 50 classes here. And you see, for pumps, there are no pumps, so this makes sense that we have a value of 0. But pants, which are much common, have a much higher IOU score. So the reason why we're having this very low values for the mean IOU and the mean accuracy is simply because we have this many classes which aren't represented or aren't represented enough in the data set. That said, we go ahead and save our current weights, and then we now dive into the next part of our work. So we've just looked at training and evaluation. Now we'll dive into evaluation with the FiftyOne platform. In some previous section, we saw how to visualize our data samples using the FiftyOne app. So if we click on the sample, for example, you'll find that
we have the original image, and then we have its corresponding ground truth mask. Now, what if, apart from visualizing this ground truth mask with the different labels, like here we have a blazer, here we have dress, and here we have a bag, we go ahead and also visualize what the model predicts? The way we could make this work is by modifying each and every sample we have in our data set. So if we get our data set head right here, we could see a couple of samples. Then we get the image using its file path. We pass this image into our already trained model. So here we have our trained model. We obtain its predictions. And then once we obtain these predictions, we create a new key in our dictionary, which we'll call pred. So we have seen that we have the ground truth. You see, we have the ID, media type, file path, tags, metadata, ground truth. We'll add pred, or the prediction. And then this prediction will simply now have a value, which will be this segmentation object. That's a 51 segmentation object, but with the difference that we are not going to create the mask path as we already have. What we're going to create here will be a mask, and this mask will essentially be our array which contains or which represents our prediction. Diving into the code, we're going to go for I sample in the data set. We want to get each and every sample and simply modify it. We are going to start by pre-processing the data. So as we had seen already, from our pre-process method, which we've seen already. So let's take off this pre-process, take this off, and then now we have sample file path. See, we have sample file path instead of the image path we had already. There we go. We now obtain the image from our sample file path. That's obviously after reading and decoding. And then we are going to also resize this image. So here we have image resizing. We resize the image. And obviously, because our model is 512 by 512, we're going to have this new size. Let's call this h underscore resized, and width underscore resized. There we go. So we have that 512. That's fine. So now we have height resized, and then width resized. There we go. So we now resize the image, and then we cast the output image into a float 32. Then we carry out the transpose. Now remember, our input images, or what we obtain from our samples, is height by width by 3. But what the model needs is instead 3 by height by width, or channel by height by width. So we want to move from height by width by channel to channel by height by width. And so we're going to carry out the transpose, which we've already been doing so far in this course. So we simply have img, our image, and then we transpose so that it suits what our model takes in, and then we modify those positions. There we go. So once we're done with the transposition, we now add an extra dimension. We have expand dimensions. There we go. We have axis set to 0. So we want to move now from channel by height by width to channel by, or rather 1 by, that's actually batch by channel by height by width. So that's it. In this case, it's actually 1 by 3 by 512 by 512. Okay, so that's it. Once we're done with that, we now normalize, and then that's fine. We can now go ahead and take off these parts where we had process annotations before, and then dive into passing our inputs into the model. So now we have this image. We want to pass this into the model and obtain some output. So here we have our output, which is gotten from passing the image into the model. So we get logits. There we go. And then now, because let's have this, because when you have, or when you get the output, its shape is essentially the batch by the number of classes by 128 by 128, where 128 by 128 here is simply 512 divided by 4. So because our output masks are going to be 1 by 128, that's essentially batch by height by width. That's obviously the output height by the output width. What we are going to do is we are going to select for each and every position in this 2D array the class with the highest probability of occurring. So to do that, it's going to be simple. We're going to take the output, which we've already had, and then we'll pass it through the argmax method. So here we have output, and then we specify the axis to be 1. The reason why we're specifying axis to be 1 here is because it's in this axis which we're going to be selecting the classes with the highest values. So here we have obviously 0, we have 1, we have 2, and we have 3. And so specifying axis to be 1 means we'll picking this specific axis out. So that's why we make that choice. Then obviously don't forget to load the model and load it with its most recent checkpoints. So now that we have this, we could now go ahead and resize our image or our output. Now remember, our input images were resized into 512 by 512 because this is what the model takes in. But then what we want to save is going to be 825 by 550 as we had as the image was originally. So we would have to resize the image and also obviously resize the masks. Now, considering the fact that our image, which we have here, is going to be of shape 825 by 550, and also the mask is 825 by 550, this means that we need to resize the mask which we get after passing this image into our trained model. After defining the height initial and width initial, which is 825 550, we could then go ahead and make use of our image resize method. So here we have the resized output. Our resized output is simply going to be TensorFlow image resize, which is going to take in our output, taking our output, and then we're going to specify that the method is going to be bilinear and that the anti-aliasing is going to be set to true. And then now what we're going to note also is the fact that this resize method takes in the output, which is 1. Like let's get back here. We've converted our output into 1 by 128 by 128, but the resize takes in 1 by 128 by 128 by some number of channels. So we need to modify that. So what we do here is we're going to add an extra dimension. So there we go. Let's have expand dimensions. Then we add that extra dimension at the end. So we have that added. So that's fine. So now we resize our image. The next step will be to go ahead and create our prediction or add that prediction into each and every sample. All we need to do is have our sample, and then we specify the key prediction, that's spread, as we had said already. And now we make use of this segmentation object where we're going to specify its mask to be the prediction, which is a numpy array. Let's not forget to specify the height and width. So here we have height init and width init. So that's it. Then since we've resized this into this new shape and that our output needs to be, let's say we've resized this into 1 by 128, or rather 825 by 550 by 1, and that we need our output to take this one off. What we're going to do is we are going to squeeze this output or this last axis out. So there we go. We have, or let's just do that below. So we have resized output again, resized output, TensorFlow squeeze. There we go, our resized output, and we'll specify the axis to be equal to the last one, so that's -1.
and then we do some casting. So there we go, we cast that, and then we specify that our data type should be unsigned int 8. There we go. So that's it. And then once we cast this, or once we squeeze and we cast, our output now will be of this shape. But again, we want this shape. That's, we want our output to be without a batch axis. So we're gonna take that off by simply specifying 0. Okay, so that's our resized output. There we go, we have resized output, and that should be fine at this point. Now, since we're done with modifying our sample, we could go ahead and save that. So we have sample.save, and that should be fine. Now we would say that if I is greater than 5, we should simply break out. So let's run that. We're getting an error, required broadcastable shapes. Now let's get back to the code and update it so that we get past this error. Getting back to the code, we notice how we carry out normalization after the transpose. So we should instead do this before. Let's paste this out here and then run this again. And with that running correctly, now let's go ahead and rerun our session. After rerunning, you could see right here that we have an additional label. That's the prediction. So we have the ground truth and now the prediction. If we run this dataset head, you'll notice we have this additional key prediction. So again, segmentation object, it has this ID, and then we note how here we have this mask. So instead of using the mask path, here we use a mask. It's the same with what we had already with the ground truth. So this means that if you don't want to specify the path, you can obviously obtain a mask and store it that way in your database. So that's it. You see the next sample, we have this mask and so on and so forth. Now we did this only for 6 samples. So getting back to our visualization, you'll notice that if we take off the ground truths, you will find that we only have this for this 6 samples. Now let's click on this one here and see what we get. We have ground truth. You could take off the prediction, or you could have the original. So this is the original. Let's reduce this so you could see it a bit better. So as we're saying, here we have the original. If you add the ground truth, you can see that we have the shirt. Let's reduce again so you could see it better. Okay, so as we're saying here, you see we have shirt, we have skin, and so on and so forth. That's the ground truth. Then for when we add a prediction, you see this is what our model predicts. So our model sees this as a shoe, sees this as pants, shirt, skin, but this portion sees it as a jacket, which makes sense since the shirt and jacket look alike. Now up here it has a hair. It doesn't do so well with the hair, but that's it. So we see how we could visualize our ground truth and our model's predictions side by side. Now if we get back to our training logs, we'll find that we had this our val or our mean IOU scores. We had the mean accuracy, we had overall accuracy, and then we had the per category accuracy with the per category IOU. So here, for example, we have value for bra, which was 0, belt 0.1, and so on and so forth. So what we want to do now is visualize our data, taking this outputs or this metrics into consideration. So what if we want to say get all the different images where our validation, or rather where our the belt accuracy, the validation belt accuracy is, for example, greater than 0.5. In that case, we would need to filter those out, and this can permit us make better decisions. So one great thing with working with 51 is really easy to implement these kinds of strategies, which can be very helpful when it comes to ameliorating our already existing solutions. So just as we had seen in our section on evaluation, we have our metrics, and then now our predictions will simply be the pred, or rather the resized output which we had from above. So we change this, we have resized output, and there we go, resized output, convert that to numpy, and then we'll put this in the list. That should be fine. There we go. We have our reference, which is our mask. So here is our mask. We also put this in the list.
But then this mask, the way we can compute it is by simply making use of OpenCV. So OpenCV imread our sample. We have the ground truth, and then the mask path. So we have the mask path. There we go. And then we obviously read this CV2 imread as a grayscale. So that's fine. So now we obtain our mask, which we pass in here. The number of labels is simply 59. So the length of label to ID will suffice. Ignore index 0, nan to num. So in case we have nan, we convert that to 0. So nan to num set to 0. Let's get back. Reduce labels equal false. That's fine. So now we've had our metrics. We can now add a new key. So sample mean IOU, which is equal the metrics, and then we specify the mean IOU. There we go. We could also do the same for the accuracy. So here we have mean accuracy, and then we have also overall accuracy. That's fine. Here we have mean accuracy, and then overall accuracy. So let's run that again and see what we get. Diving back into our visualizations, you notice that we now have this extra primitives. So here we have the mean IOU. We also have the mean accuracy, and then the overall accuracy. So for each and every sample, we have these different values, and so we could filter out the different samples which have a certain overall accuracy, for example. So let's look for samples with an overall accuracy between 0.81 and 0.92. You see that when you filter this out, or when you select this, you have all these different samples. So 9 out of 77 samples have an overall accuracy of between 0.8 and 0.92. Now we can go from 0.89 to 0.92, and you see we have only a single sample. So this turns out to be our best performing sample in terms of the overall accuracy. So it's normal that the ground truth and then what the model predicts will be quite similar. See that we have what the model predicts, and then we have the ground truth prediction. So that's it. Now let's try to get that for the IOU. Let's take this off now. There we go. Let's get back to the IOU and filter this off. You see again here we have one. We have this one. Let's see. Okay, you could notice that the sample which performed best in terms of overall accuracy isn't the exact same sample which performs best in terms of mean IOU. But still, normally these two samples should have their ground truths and predictions or model predictions quite similar. There we go. Let's take off our prediction. See, this the ground truth, and then this is what the model predicts. That's fine. We could check out the mean accuracy, and we could also check out, let's cancel this, or let's reset this. You see, you could reset, and then we could also check out those with the worst overall accuracy. So let's check out those with the worst overall accuracy. We have 5 of them between 0.09 and 0.19. We can click on this one and see how poor our model performed on this one. So here's our ground truth, and then here's our prediction. You see that this prediction here, it predicts all this to be pants, whereas the ground truth expects that this should be a romper. Now this makes sense since we shall not get the romper very often in our data set. So the model hasn't learned to classify this kind of dress as a romper. For the shoes, here we have shoes. Let's see what the model predicted. It did well with that. Hair, let's check that out. It wasn't bad. But what really makes this or what gives this a very bad score is just the fact that all this is a romper, whereas the model sees this as a pant, and this two, well, this is as a blouse. So you see here we have blouse. So all this blouse and then your pants, which isn't too different from what we would expect, but this as ground truth is a romper instead. So that's it. We could check out this other one. Let's check out this other sample. We take off the prediction. Here, this is a blazer and a shirt. Check out the predictions. This is a coat and a coat sweater. So you see, that's why the model score is quite low. You could check out the score here. The mean IOU is 0.047. The mean accuracy is 0.27. The overall accuracy is 0.093. So that's it. Now, what if we get for each and every sample the mean IOU for every category or every class? So this means that for a class like shoes, we could get the samples which have the worst predictions for shoes and those which have the best predictions for shoes. So let's go ahead and modify our code such that we don't only get this mean IOU or overall accuracy, but also a more specific IOUs for each and every category. So now we'll go ahead and modify the code or update the code such that we would have the per category IOU added to our visualizations. Right here we'll go through the per category IOU which we obtained from the metrics. So just like the mean IOU which we get, we could also get the per category IOU. So for, let's say, C in metrics, we get the per category IOU. There we go. If the value of C is greater than 0.001, we are going to create a new key, because just like this we had a key and then we have corresponding value. So we'll create a new key and then we'll give it a name. What we want to have is, for example, shoes underscore IOU. So that's what we want for our keys. So here we have ID to label, we have K and C, then enumerate. There we go. So that now for each and every category we have its corresponding ID, and so now with ID to label we'll be able to get its label, ID to label plus underscore IOU. So we can have, for example, we could have shoes IOU, and then now we have sample shoes IOU, which is simply equals C, because here we get in this per category IOU. So here we'll take this off now and replace with key. So that's fine. Let's run that again and then go ahead and check out our visualization. We now find that in addition to this mean IOU, mean accuracy, and overall accuracy, we have the different IOU scores for each and every category. So let's pick out one category. Let's say shoes. There we go. We click on shoes. You see it ranges, all the scores range from 0.05 to 0.8. Now let's select between, say, 0.73 and 0.8. See here we have 10 out of 77 samples get an IOU for the shoe between 0.73 and 0.8. So let's click on this first one, and then we could swap between the ground truth and the prediction. See, ground truth, you see, there we go, makes sense. We have here shoes, and then when we take off ground truth, although we missed out with the romper, for the predictions we have shoes, which is well predicted, unlike the romper. So that's it. We could select another sample. Let's pick out, say, this one. We could take out the ground truth and the prediction. This is original with the ground truth. So here we have the shoes, and then the predictions. We also have the shoes well predicted. Now what we could do also is, let's take those which don't have shoes properly predicted. So now it's between 0.05 and 0.16. So there are only 3 samples. So it turns out that the shoes in general are well predicted as compared to some other samples which are less represented. So if we click on, let's say, well, just looking at this in general, you would notice that most times when the shoes aren't well or correctly predicted is when the person is putting on a clothes or a dress which covers the shoe. So if you click on this here, you should have this. You see, let's take this off, take off the predictions. You see, we have just this little tip here. So that's where we have problems with predicting the shoe. So if you want to ameliorate the shoe prediction, you would have to train on more of this kinds of data. Let's look at the prediction. You see, it picks out just this part. Let's click on this, zoom, there we go. Okay, so you see it picks out, sees his back, sees his boots, bracelets and blouse, all of that. So that's not really good. If we click on the ground truth, obviously you just have their shoes. So this tells us that with these kinds of samples, our model struggles to notice that this is a shoe. Now if you move to the next one, we also have a shoe, although it doesn't cover, or the dress doesn't cover the shoe here. Maybe because of the size of the shoe or the kind of shoe, we don't predict, or because unlike the others where we had some closed shoes, here we have a ballerine where you have the skin which occupies much part of the zone where we usually have the shoe. So here we have skin according to the prediction. Here we have shoes, but it doesn't see this part. Now if we move to the next one, because there are 3 samples, if we move to this next one, we should take off the prediction. You see again here that the shoes isn't very visible. So the ground truth, here we have shoes, where we take that off. But actually normally the ground truth here should have skin, because here we have some part of the skin. So the sample wasn't properly annotated. Nonetheless, what we predict here, we take off the ground truth. You see, it predicts shorts, predicts shoes, shorts. Well, it doesn't do very well as it's supposed to do. Also, as we've said already, because the trouser covers the shoe and it's not a closed shoe like the other samples we have in our data set. So, well, when it comes to ballerines and say sandals, we would have more work, or we would have to gather much more data with respect to that. Now let's pick out some other, let's say hat. We could pick out, let's reset, we could reset here, could reset, that's fine. And then we pick out, let's say hoodie, or we decide to pick out hat. So that's it, hat, from 0.01 to 0.38, meaning that it doesn't, the model doesn't perform so well when it comes to the hat. So let's increase this. There we go. We should get the number of samples. We only have a single sample which does a little bit better than the others. So let's take off the ground truth, take off the prediction, see the original image, and then try to compare the ground truth and the prediction when it comes to just the hat. So there we go. We have ground truth. See, we have hat here. Take that off. We have prediction, and you see it takes hat, but see some parts are skin. So that's it. So it confuses between the hat and the skin. So overall, we see that the model struggles to predict the hats correctly. Though you could see with the shoes, does quite well. Now that's it. We've seen how to filter the samples based on a specific category's IOU, or based on the overall IOU, or rather the mean IOU, or say the mean accuracy, or the overall accuracy. Now we're going to move to the next section where we shall be generating new samples. In the section on generating new samples, what we're going to be doing is essentially taking in an input image like this one, adding this up with a mask. As you could see here, is specifically the boot. So if we take out just this part and just this other part from the input image, we have this mask. obviously our model can generate this. So if we take this, pass this into our trained segmentation model or Segformer model, we can obtain this mask containing only the boots. And with this prompt, we pass this into our Inpainting model, which is available in the Diffusion's library of Hugging Face. We could obtain a new sample where we've modified the region where we have the black boots. So we go from this black boots to this red colored boots. And so given that we have the input image, or we could get some input image from our val data set, we've trained our Segformer model, and obviously from this tool we could obtain the mask. And then we also have this prompt. It means that it's now very easy for us to generate or edit our images in this kind of automatic manner. Now it should be noted that the mask generated by the Segformer model obviously will contain the other parts of the image. So you would expect to have pants. So let's change the color. So we would expect to have pants and not just only the boots. So if we were to pick out only the pants, then we would have this zone picked out. We would have this zone 2 picked out. But now that we're dealing only with the boots, that's why we've picked out only this zone. So what we'll do now is we'll write code which will take the output mask generated from the Segformer model and then only pick a given class. So all the other classes will be sent or will be turned to zeros, and then only that specific class will be given a value of 1. And then we'll obviously have a prompt related to the class. So this means that if we wanted to deal only with the pants, or if we picked the pants on the mask here, then we'll change this boots and then we'll replace it with pants. So instead of boots, we would have a red colored pants. Obviously we could change the color, so we could say a green color pants. We could modify the whole prompt and obtain our desired outputs. So this is how easy it is now to edit our images once we have a trained model. Now let's dive into the code and see how we could generate this mask when given an input image like this one. We'll start by our generate inputs method, which will take in the input or the image path and then a specific mask ID. So that's it. Now if we do label to ID or ID to label, let's check out all the different labels. We have boots. Boots is actually this here, 7. So when running this, we're gonna specify 7 because we want to be able to edit our input image based on the boots. Could check out this image 0003. See, it contains boots. Now make sure that you have or that a specific ID matches with what you have in the image. So that's it. There we go. We have written this out. So that was it. We have our source image, which we can read with OpenCV. Here we have the image path, and then we have the mask. So our mask, the way we get our mask is by simply taking our model which we've trained, we pass in, and then we pass in our source image. So we pass in the source image to obtain the output. Now note that we need to carry out some pre-processing, so we need to modify this code such that we have the pre-processed source image get into the model before we obtain the mask. That said, copying and pasting out the code which we've written already. Here we have our image. Instead of sample file path, we have the image path. Take this off, and then we resize, we cast, we normalize, and then we get the transpose, we expand, we add the extra dimension, and then we obtain the output. So we return our source image, and we'll also return our output. We could go ahead and test this out. So let's create this new cell, generate inputs, and then we specify that we'll specify the path, and then the mask ID is 7, as we just seen. So let's run this and then see what we get. We get in this error, transpose expects a vector of size 3, but input is a vector of size 4. So let's get back to the code and see what we have there. Well, let's first of all take this off and then run this again. Then what we'll do now is take off these 2 dimensions and resize our output. So once we get the output, we are going to do the argmax to get the category with the highest score. Then once we get this argmax, we resize our output, and then finally we take off the batch dimension. So now we have our resized output. Now we could there we go, we could check out this resized output. So instead of output, now we have resized output. Let's check that out. We now have the right shapes, so we could go ahead now and create this mask where all the other regions are black, while only this part where we have the boots is actually white. So what essentially we want to do here is say all this region or all the other regions will take up values of 0, while the rest, or rather while where we have the boot, will take up value of 255. So that's exactly what we want to do. Now that said, let's consider that we have this input as masks, or as our mask generated by the model. Now obviously here you see that all the different values take up we have different values except for this position here where we have the value 7. Let's change the color. There we go. Okay, so all through we have different values except for this one where we have the value 7. So it's similar to the scenario here where we could have different masks or different mask values generated by the model, and then for a given region like this region we have the value 7. So we're just simplifying it this way. Now what we could do to take this 7 to 255, want to send this to 255, and we also want to send all the rest to 0. So what we'll do first and foremost is add this with -7 times ones. So we will have 1 or ones which take up the exact shape of our input. So here if we do this, if we add this up like this, then what we'll be getting will be another matrix. Let's draw another matrix below. So our output matrix now will be such that we would have values or all other values different from 0. So here this x is different from 0. So here we would have x, 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 x, and then at that position where we had the 7, because we're subtracting with 7, then we are going to have a 0. So all through here we have x and x. Let's change back the color, take this, and then see here we would have a 0. So all these values, both positive and negative values, they could be positive as well as they could be negatives. It doesn't matter. They are all different from 0, except for obviously this position where we have the 7. Get into the code, we're going to define a mask. So here we'll define a mask, and now this mask will be such that we will take in our resized output, and add that plus negative the mask ID. So it's like doing -7. There's this part. So this is the resized output here. This is the mask ID, and then this is some ones which take up the same shape as the resized output. So now we would have that mask ID plus, or rather times the ones, or ones like, it's actually ones like our resized output. There we go. So now we take this and add with this. We expect it to have this kind of matrix where we have all different values except for here where we have a 0. Now getting back to our illustration, the next step will be to give this a value of 255 and then all the rest a value of 0. So first things first, given that we have both negatives and positives, what we could do is we could multiply this by itself, or better still, we could square this. Well, saying square will be confusing this with matrix multiplication, but essentially what we're saying is, let's copy this, so we'll just paste it out here. Essentially what we're saying is, we have this square, let's take this up, this 2 off, and this other 2 off. There we go. So what we're saying is we're doing an element wise multiplication, so it's not matrix multiplication. We take this value, multiply by itself, and so on and so forth. Now obviously again, all the values will still be non-zeros except for here where we have 0 times 0, but with the difference that now all these values are positive. So x now is going to be strictly greater than 0. So we go from x being different from 0 to x strictly greater than 0. So we would have a new one here, space that out, copy this, and there we go. So now our x, in this case our x is strictly greater than 0. Take off this 2. Okay, so that's it. We now have this new matrix, and then the next step will be to multiply this by a very large number. So let's say we multiply this by 10 to the power of 10. So if we multiply this by 10 to the power of 10, and then we clip the output to in such a way that the max will be 255 and then the mean will be 0, then what we'll be getting now, let's take this off, what we'll be getting now, that's after the clipping. So we multiply this, all these values by 10 to the power of 10. So after multiplying by 10 to the power of 10 and then clipping such that the max is 255 and then the mean value is 0, we would obtain a new matrix. So let's copy this again and paste it out here. So we would obtain this new matrix, and this new matrix now will take up values of x. Would have values of x being equal to 55. So all the values of x are now equal to 55. And so finally what we could do is, if we subtract by each and every value here, if we subtract 255 from each and every value, then all these values now, or all these values of x now become 0, and where we had 0 it becomes negative 255. Obviously to convert that to 255 we just simply need to multiply by negative 1. So now if we subtract by, or we remove negative 255 and then we add a negative sign here, so now we would have all zeros, because we've subtracted 255 from all those values. But here we would have 255 and all the rest zeros, all this zeros, and here 0. So that's how we can simply convert this input mask to this mask where we have only zeros for all the non required regions, or for all the regions where the category we want to work with isn't represented. So getting back to the code, we're going to implement this. Obviously we've already done this first part, so we already now have this this matrix. So let's go ahead and multiply by itself. So we could do our new max now. It's simply going to be multiply by itself to make sure that we only have positive values. So we have mask, and then after multiplying by itself we multiply by a very large number. Let's get back to the code. We multiply this by a very large number. We'll have 1e to the 10 times this mask. So now we've multiplied by that very large number. The next thing will be to clip. So just as we have seen here, we're going to clip and make sure that our values fall between 0 and 255. And since obviously all the values will be greater than 255, they would come down to 255 and only have the zeros which will remain 0. So getting back to the code, let's reconnect. Getting back to the code, we have np clip, and then we specify our mean and the mask and the max actually. So here we have the max, which is 255. There we go. So that's it. So now we've clipped. Getting back to our explanations, the next thing we want to do is subtract 255 and then multiply by a negative 1. So, or what we could do is we could simply take 255 minus this.
So let's get back and just do 255 minus that. Okay, so now we have our mask. And then after obtaining the mask, let's print out the mask shape instead now. So after obtaining the mask, what we'll do is we'll use OpenCV to write this so we could check that out. So in write our mask GPG, and then we have mask. Okay, so let's run that and see what we get. Now we open up our mask, and normally we should get, we're getting this instead of what we expect. The reason we are getting this output instead of, say, the region specific to only the boots is because the model doesn't perform well with categorizing this region as boots. So let's check out shoes. If we go shoes, there we go, 39. So let's replace that ID with 39 and see what we get. Let's see, 39, run that again and check out mask. Normally you should get that because the model confuses the boots with a shoe. Let's close this and check that again. There we go. As you could see, now we have this region 39, which is all in white, while the rest is in black. So that's it for this part. We're able to generate our inputs as we had seen already from our initial schematic. We have this input, we have the original image, and then we have this region. Now the next step will be to carry out the inpainting. That is to take this input image, pass into our inpainting model, and then edit our input image such that we have this new image. The exact inpainting model we'll be using will be the Stable Diffusion 2 inpainting model from Stability AI, and which is made available on Hugging Face via its diffusers library. So as usual, when working with Hugging Face, you have this simple examples which can help you run the code very easily. So here we have how it works. You see, you can have an image, you have the mask, and then you have some output. So let's go ahead and test this out. Here we have some notes. Despite not being a dependency, we highly recommend you to install Segformers for memory efficient attention. That's better performance. And if you have a low GPU RAM, make sure to add pipe.enable attention slicing after sending it to CUDA for less VRAM usage to the cost of speed. Okay, so that said, let's simply copy this. We've already installed this, so you could also copy this and install, but we've already installed this, so we'll simply copy this and then get back to the code. From the code we copied, first thing, we are going to import the Stable Diffusion Inpaint pipeline from the diffusers library. Then we create a simple pipeline specifying the exact model ID. That's from Stability AI. Then the PyTorch data type is float16. We are going to be working with our GPU, so we have pipe to CUDA. Then we specify the prompt, but we're going to get back to this. Now it should be noted that as we had seen in this model card, we're told that, let's scroll down, we're told that despite not being we recommend you installing the Segformers for memory efficient attention. So we're going to do this immediately after we send this to CUDA. So let's save this. There we go. So that's why you see we have this extra line right here, which was not in the model card. Then from here we have the image which has been generated using the prompt, using the original image. It turns out to be a pill image as specified here. Then we have the mask, and we generate the images which we can now then save. So essentially we're taking in an image, we're taking in a prompt, we're taking in a mask, and then we're generating, or we're editing this original image and generating a new image from our edited image. So that said, we need this image and the mask image. So we're going to call on our generate inputs method. Let's copy this here. There we go. We call on our generate inputs method. And then here we specify 39. There we go. And that's it. So now in our generate inputs method, we
we output numpy array, so we need to convert this into peel images. So that said, we have image from array. That's our source image. Let's take off the shape. We have the image from array, and we also have the same image from array. And then we take off the shape. There we go. So now we have our peel images. Let's run our generate inputs and see what we get. There we go. Let's have this image and then mask image, and there we go. So let's run this and then see what we have as output. But before running, let's update the prompt. So instead of face of a yellow cat, let's say we have red colored shoe, because this is shoe, high resolution, and let's take this off. Okay, that's fine. So we have red colored shoe, high resolution, and we're gonna save this in let's say shoe. After running, as you could see here, we have the shoe, which is not really that red. Maybe it looks more brownish. And then you could also compare with the original. So you see that there's that editing which we've done on the image. Now the image size could be changed, so we could resize our image so it looks like the original. Now let's modify again. So before we took this the mask ID to be 39, let's take 13, which will represent the code, and modify the code. So let's say we have a green colored coat, a green colored nice looking coat, and let's run that again and see what we get. Well, normally we should separate this so we don't have to always create the pipeline each time we run this. So we'll separate the part where we create our pipeline with where we actually generate the inputs, or rather we actually generate the new image. So let's go ahead and paste this out here. Then before running here, now we have code. So we have code, there we go. And then let's run this. So we already have our pipeline, then we have now this code. Then we're gonna go ahead and resize our output. So here we have image resize, we have width in it, and then height in it. So instead of height width, we have width height, and that looks fine. After resizing, we could just simply display and then visualize that. So let's run this and see what we get. We get this output, but we don't have that green color, so we're going to modify this prompt a little. Here we say photorealistic, because here we were just green colored nice looking code, high resolution, without taking into consideration the whole image. So we have a photorealistic photo of a woman wearing a green colored coat, wearing a green colored say nice looking coat, high resolution, and let's say all green, high resolution. There we go. Let's run that again and see what we get. While that's running, we could change this to code, and then we modify the code of generate inputs such that this takes in the mask label, and then here we'll define mask ID, label to ID, and mask label. There we go. So when we pass in code label to ID, we produce the ID, which in this case is 13. So let's get back. You see, now it's much better. We have a code now which looks much more greener as compared to what we had just seen before. Let's run this again with the modifications which we just had, and we've already run this. Let's run this again and see what we get. We have our edited image only on this zone, and that's it. So we've just seen how we could go from an input image, which is this input image right here, to an edited version of that image based on a specific mask which was generated from our trained Segformer model. In this section, we've just seen how to create or how to edit existing data and create new data from that already existing data. Now this data may be data the model has seen already, or data the model has not yet seen. We're going to move to the next part where we are going to look at data augmentation, and we'll end this section by creating a plugin with FiftyOne. That's essentially a FiftyOne plugin. So the idea of data augmentation here is we have, supposing an input image like this one, then we edit this image. In this case, you see how the boots are edited. You can see this. And then in this other example, you could find that the code is edited. So what we're saying here is we take an input pair like this one, which is essentially composed of the input image and its corresponding mask, and then we edit this image so that we have this new image. We also can create this other new image, and then we repeat the same mask. So we take this mask and then we simply repeat it. So now you see that we're going from one sample to two other, or to three samples. So we triple the sample number by simply editing this image. Now it should be noted that after editing this specific image right here, we could go ahead and carry out the editing on this one. So we could end up with an image where we have the boot turned into red, the coat turned into green, maybe the sunglasses changed into some let's say red sunglasses, maybe the person's skin turned into black, and so on and so forth. So we must not always edit from this original image. That said, this way of creating new samples or augmenting our data via editing like this permits us create much better and diverse augmentations, as now we could even change the background. So we could decide and change this whole background. We change each and every region here, and we have a whole new image. We could even change the person's face, and say for example we want a man. So now you'll be getting a different background. You get a man-like suit, although a man could put on this kind of coat. You could change the hairstyle and so on and so forth. But nonetheless, it should be noted that the shortcoming of this method, especially with a technique like or especially when dealing with segmentation, is that the newly edited image may not match with the mask. So we may end up with a slightly noisy data set. That said, let's dive into the code and see how we could create our new data samples from our original data set. We can now get back to the code, and you should note that the code for the data augmentation is going to be very similar to that of the image editing. As here, the only difference is, unlike with the image editing where we have the model, like here we had the model which predicted the mask. That's our trained Segformer model which predicted the mask. We are going to make use of the already existing mask for a given data point, or for a given input image. So if we have an input image like this one, we'll make use of its corresponding mask, which is given in the data set to generate this mask, which will then be added with a prompt passed into the Inpainting model to create a new data point. So again, here we have the same model ID. We have this create pipeline, which essentially is the same we've seen already. Then we have this generate inputs, which is different from what we just saw on the image editing. And you'll notice that the difference here lies in the fact that we take off this part which includes the model. So all this resizing, we don't really need all this. That's, you see here, we resize, we normalize, we pass into the model, and then we resize again before creating our mask. But since our data or our data set already comes with this, we take off all this. So getting back to data augmentation, scrolling down, you see here we have the image path and the mask path, which is passed in together obviously with the mask ID. So in here we have the image path. You see, you read that image path, you have the source image, you have the mask, which is also red, just as the image path was red. This is red from our data set. Then obviously specified as grayscale. Then the same processing we did previously to select a particular category is what we repeat here, so no change in the code. Then we convert this to peel images. So that's it. Once that's done, the next step will be again similar to what we saw with image editing. So here under image editing, we simply make use of our pipeline, and then we pass in the prompt, we pass in the image, the mask, and then we got our output image. So it's the same thing we're going to do here. Let's scroll down. Here we have the our pipeline. We pass in the prompt, but now we have this two parameters which we've added: the guidance scale and number of inference steps, and the generator. Now it should be noted that we could also do the same. We could also add this here in our image editing. So we could add the guidance scale, and we could also add the number of inference steps. So these three extra parameters have been added. Now this guidance scale shows the model how much it should add there to the prompt which we've passed in here, and also obviously increases, or as we increase this guidance scale, increases the image quality. Then for the number of inference steps, if you want to higher or increase the number of inference steps, increases the image quality, while reduces the image quality. Nonetheless, stable diffusion works well with even low number of inference steps. Then for the generator, this is for reproducibility. So if we set your random seed, or if you set your seed to 10, then each and every time you generate the exact same image. So that's it. We have the usual image and the mask. Then one thing we want to do is we want to add this number of images per prompt, meaning that for every time we call this Augment method, we could say, for example, we generate 10 images, and that's it. So we put all this in a list, and then we return a value. Here we're just taking in we're just taking out from this just a single one. So we could take this off and retrieve all the edited images. The next we have this hash method, which essentially produces a value like this one. And the reason why we need in this method is simply because here when we create our extra data, let's say we have this extra data, let's have this here, let's say this is called 0003. Let's increase the size to say 100. Okay, so let's say this is called 003. Then in that case, if we want to create some extra samples, or if we want to augment our data, we could call this 003 now underscore the hash value we had from here. So we could copy this, get back here, and paste it out. There we go. So this will be the file name for this new data. So we have this copied, and there we go. Let's just change this a little. So we could say this is E. There we go. So now we have these three samples with three different file names. So that's essentially why we need this hash. That's fine. We'll just keep this part and then go straight into this transform sample method. What the transform samples method does is it takes in a sample from our 51 data set. It takes in the category ID, or the specific category, in this case code. It takes in a prompt, and then it modifies that sample based on the prompt and the corresponding category, then creates a new sample which is then added to the original 51 data set. So looking at this method, obviously we have the hash which we create, and then we have our pipeline which we get using the create pipeline method and the model ID, and passing the model ID into the method. And then now we generate our inputs, which we get into our Inpainting model. So the way we generate our inputs is simple. Since we get a sample from our 51 data set, remember our 51 data set, which we've seen already. So we could get back here. You see, this is our 51 data set. Let's scroll down and then get back to the code. So as we're saying, we have, let's
let's just do dataset head, so we could get some samples. There we go. You see, we have this sample, and then from here we could get the file path. So as we're saying, here we have this file path, which we pass into our generate inputs method, which will permit us generate the image and the mask. Not forgetting the ground truth, or rather the mask path. So again, here you see we have a given sample, we have the ground truth, mask path. That's it. So we specify this too, and then we obtain the input. So if we get back here, we had seen that to generate this, we needed this image path, we needed a mask path, and then there's mask ID. Now this ID will depend on the specific category you want to modify when carrying out the augmentation or the editing. So here we have the select class. In this case, if it's code, then label to ID, we convert that into the specific ID. So if it's code, then we should get something like 13. So that's it. And then now we pass this inputs into our augment method. So here we have our pipeline, we have the prompt, we have the image, we have the mask, we have the guidance scale, and we have the number of inference steps, which we pass into our augment method, which we've seen already. And now that generates the images. So we now have our newly generated images. The next step will be to add this into our data set. So we'll simply write this into our data set. I have the samples file path. So if we have a file path like this one right here, no, rather this one. Let's say we have a file path like this one. Let's copy that, so we could better illustrate or better show you what exactly is going on here. If we have this file path, then we'll take off 1, 2, 3, 4. Then we add the underscore, we add the hash, and then we have dot png. There we go. And then we write this this output, which is from our augment, as the image which we get from our augment method as an edited or augmented image, is what is written in this file path. So now we will not only have image 0018, you also have image 0018 hash png. Now because we do this for the images, we must also do the same for the png masks. But for the png masks, it's just a copy. So we'll just copy what we have in this mask path. So we'll copy this image here, or this mask, into the same folder, but with the difference that we're going to change its name, its file name. So we add this hash here, the same hash we used here. So let's take this off. That's it. And then now we could display our output, and it doesn't suffice only to say copy this new data into our data set. We also need to create a new 51 sample. So to create this new sample, here we have the file path for the image. Obviously it's going to be image 0018 underscore the hash.png. So that's it, the same one we have here. And then for the ground truth, we specify that it's segmentation. So we expect to have a mask or a mask path. And so here we have our mask path, which is the same path we have specified here. So now having this, we're telling 51 that we have this new sample, and then here we're going to simply just add this new sample into our original data set. So let's run this and then see what we get. After running, here's the output we obtain. You can see we have this green code. That's fine. Let's go ahead and check our data set. Let's increase this so we could see this better. So you see we have this new mask added, and also we have this new image added. Click that, and then you could check out the mask. So now at this point we have our image and its corresponding mask. Let's go ahead, or let's get back to our 51. Let's get back to visualization and run this again, so we could see if this has been added to our 51 data set. Scrolling down our data set, you would find that we have, first of all, here at the top, you have 78 instead of 77 samples as before. If you keep scrolling, you will find this extra sample which we just added. So this is a sample which now has been modified, and this is what we get. So we click on that, and let's see what we get. Okay, so you see we have the sample, you see the green code, and then you have its mask. Now what if we want to change this, or we want to modify this edited sample such that we have red boots? We could simply get back here. So here we have boots, a photorealistic photo of a woman wearing a red colored nice looking boot, all red, yeah, all red, high resolution. Okay, so that's fine. Now since we want to update that specific sample, let's get back here, dataset dot head, or rather dot tail, that's the end. Let's see what we get. We have all these different samples. Now we'll say if our sample ID, because I think, yeah, this is it here. If our sample ID is equal this value, so if this is our sample ID, there we go. If this is our sample ID, let's take that off. If this is our sample ID, then we are going to run this. So we're going to create a new sample and add it to our data set. We don't need a break this time around. So that's fine. Let's run this again and see what we get. So if this is equal that, then you should run that. So after running, you could see we have this new sample with the red boots and with the green coat. Now this is reproducible by just specifying the exact same seed. Let's take this off, get back to our visualization and run this again, and re-visualize our FiftyOne dataset. We've now moved on to 79 samples. That's from 78 as we had previously. Let's scroll down to this bottom and click on this, and now you could see that this other sample has the boot changed and also the code. So now we have this new sample, which is a modification of the previous modification actually. So this was a previous sample, we modified this and we got this one. Let's reduce that a bit so you could see clearly. So as we're saying, we modified this and then we got this new one. Now you're getting a blue instead of red, so let's modify the way we save the image. We're not going to use OpenCV to save our image. Here would instead do image which was saved is going to be the output. That's this output, which is in the PL format, PL image. We save this directly without converting to a NumPy array and saving with OpenCV. Let's take that off and then rerun the code, and we should get something now better. Now we could modify this our seed. So let's change the seed to say 100. Let's run that again so we could get a different boot. There we go. We have this new output now. Let's go ahead and check and rerun our or refresh this so we get our new data set. This is our new sample which has been created. Let's go ahead and take this off. You see we have those boots, and that's fine. So that's it. As we had said already, one disadvantage of this method of data augmentation is that it produces noisy data. So the input image, for example, which had only this portion to be a purse, now has this whole portion with a purse. So this labels this section wrongly. Now what if instead of having to get to the section, run this different code, and then have to get back here, refresh, and get our new sample, we just make use of a plugin like this one, which will permit us augment our data very easily. So let's see how that works. You see here we have error occurred during operator execution, and the reason why we're getting this is simply because we haven't selected any image. So let's suppose that we want to augment this image. We click on a given image, then we get back here to this where we have this browse operations. We get back there, we select the plugin. See here, we select this plugin, number of augmentations per sample. Let's say we want to have 5 augmentations. We want to select a given class. Now the classes which we have here
are only those found in the given image. So if we picked this image, if you pick this image, you find that we have a vest, we have t-shirt, we have shorts, we have skin, we have shoes, we have sunglasses, we have hair, and then we have accessories. So if we get back to our plugin, again here among the classes we have bag, hair, shoes, shorts, skin, sunglasses, t-shirt, vest, and accessories. So let's get back to this. We have 5, and then the prompt is let's say we want to update or want to modify the vest. So let's get back here and take out this prompt which we had already used. So let's copy this prompt, get back to visualization, modify, let's scroll down, and then modify or include this prompt right here. So here we have, it's actually a man, so we'll say a photorealistic photo of a man wearing let's say a blue colored nice looking let's say Gucci vest. That's fine. So that's fine. All blue and high contrast. So you find that instead of having to go and check manually the different categories which are found in that given image, you can automatically generate it from here or make use of that already generated, and then you specify a number of inference steps. So 50 is the default value. We'll set it, we'll leave it at that. The default guidance scale here is 7. We could increase the guidance scale to say 8. Well, we have steps of 2, so we take 9, and then a random set of 10. So let's execute that and then see what we get. While still pixelating, we could check out our data because obviously it's already saved. So we scroll down, we get to this point. You see, we would have the original image. See it right here. Let's reduce this so you could see better. We have the original image, and then we would have this augmented samples. We chose 5, so that's why you have 1, 2, 3, 4, 5 different samples. Now the only difference, you have 0, 1, 2, 3, 4. That's it. So you see this one, that's blue Gucci vest. That's fine. There we go. So this is original. These are the other samples. That's it. We have this other one, not really blue. Then we have this one, that's blue. Although it doesn't occupy exact same region as the original. So that's it. And then we have this other one, that's blue. And then finally we have this other one, which looks more like what a Gucci vest would look like. That's still blue, so that's fine. So this is some extra samples which we've added onto our data set. Now we are going to dive into how to create our own plugin, like the one we just used. That's actually simplifying our work and also helping others in the community easily create this or augment their own data set. So obviously a plugin is used or could be used in many other different cases, but in our own case we're using it for data augmentation. Now let's get back here where we'll see how to download plugins. So there are 2 plugins I'm downloading, although I just need just this one. So here we have this plugin which we download. Is situated in this GitHub repo, and then here is its name. So here we have in this GitHub repo data augment, and with its name we simply download that, and then we get to use it as you saw us use it before. So let's get into the code. That's the code you have here is the exact same code you would have or you will be downloading to make use of the plugin as we had seen already. So getting here, the only difference now is we have neural learn, and here we have neural learn. So that's the only difference. So we have this different files we find here. Let's increase this so you could see better. So we have the assets. See, the assets just contains the icon. Then we have the init file. We have the gitignore file. Well, we actually need just the init file. We need this FiftyOne YML file. We need the requirements of txt file, and then we have this Python utils file. Now let's start with the 51 YML. So essentially here we're just describing our plugin and saying what it does. So here we have the 51 version which we're using. We have the name, neural learn, data augment. We have the version of our plugin, so we could say 1.00. That's fine. Then we have description, test out various these are not augmentations. This is going to be augment segmentation data set using stable diffusion Inpainting model. That's fine. So that's the description of our plugin. Take this off, and then we have the URL. That's this GitHub URL right here, and then we have different operators. Now we're going to check this out in our init method, or rather in our init file. So we have this init, and in this init we'll see that at the end we have the different operators which we could register. So we're registering this SD, that's standard stable diffusion augment operator, in our plugin. Now this stable diffusion augment, if we scroll up, we have this property, we have this config method, and here we specify this name, augment with standard deviation, or rather with stable diffusion Inpainting. If we get back to 51, you see it's the exact same name which matches with that. So we are looking at how to create our own plugin. Essentially most of what we'll be doing will be in this init method. So we could dive into, or let's just dive into how the plugin is created simply. Now in this config, here we have this operator config. We specify the name, we have a label, we have a description, and we set dynamic to true. Then we have the icon, so that's in our assets, icon SVG, that's it. And then we return this config. So that's it for the config. Now we have these two methods which we are using. That's a resolve input, this resolve input method, and then we also have this execute method. We're not really using this resolve delegation method. When we get back to the plugin, you will find that we have this interface right here, which makes our work really easy. But this interface needs to be pre-designed, and where we actually pre-design this interface is in this resolve input method. So this acts like our front end. Let's reduce this so you see that clearly. So in our resolve input method, that's this resolve input method acts like our front end, while the execute method now acts like our back end. In this resolve input method, we're going to create this form view. Now we'll specify the label and the description. So here we have augment with stable diffusion Inpainting, and description apply stable diffusion Inpainting to an image mask pair. Getting back here, we have apply and stable diffusion Inpainting to the image mask pair. So that's it. So just as in the code, we had the label augment with stable diffusion Inpainting, and here we also have augment with stable diffusion Inpainting. So that's the label, and then the description is shown just right here. So that's it. We've created our form view. The next step will be to get all this data from the user. So if we get back to the code, you will find that here we have this inputs, which will specify this one will specify it to be an int. So here we have number of augmentations per sample. So that's number of aux. This is very important because we will be using this in the back end. So you have to be careful with this. Then the label, number of augmentations per sample. If you check this here, you see we specify number of well, this is it here, number of augmentations per sample. And then we have the description, the number of random augmentations to apply to each sample, which is exactly what we have here. So that's it. And then because it's an int, you have this option. You see, you put let's say 2, or if you increase, you could increase. See, it takes the integers. That's fine.
auto takes negative too. So we should fix this, or you could try to fix this and make sure it takes only positives, or you could take negatives and then you return an error in case it gives, or you take as input a negative here from the back end. Now for our next, we have the class. We're just going to skip this and get to the prompt, and then we'll get back to this, since this is a little more complicated as compared to all the remaining inputs. So we have the prompt. If you get back to the code, you see here we have prompt. Let's scroll through all this here. We're not going to take this into consideration for now, so keep that aside. We have the prompt, which is a string, which makes sense. So here we have prompt. We have the label, and then we have the description. So it's required, so we'll set that to true. That's it. Now all this normally should be required, so we could modify this here and set required and set to true. Okay, so that's fine. Let's continue. We have the inference, or the inference steps, number of inference steps. Here you have an int, and then the default value is 50. So that's it. We have the default value set to 50, and then the view. Now the view here is different from what we had with the prompt and what we also had with the int, or what we have with the number of augmentations. So this view here is different. The difference here is that we are having a slider. So here we have this inference steps slider, which we've created from here, but it's actually a slider view. So with the form, or rather with the int here, with the number of augmentations, we had a field view, whereas here we have a slider view. Now we're going to specify the mean value. Obviously we have the label, we have the mean value, it goes from 50 to 200, and number of steps is 10. So we go from 50 to 200, and we go through steps of 10. So that's why when you get here and you increase, you see you go from 50, 60, 70, and so on and so forth, up to 200. So that's it. Then that's it. We move to the next. We have the guidance scale, is similar to what we've just seen. Now this is a slider again, and then we have mean value 1, max value 30, steps of 2. So that's it. And the default is set to 7. That's why if you notice here, our default is set here to 7. See slides, we go through steps of 2. That's fine. We have then the next, our random seed. So for random seed, we go from 1 to 1000 with steps of 1. The default is 10. That's why we get here again, you find the default to be 10. Okay, so that's it. Now getting to the class, if we get back to the class, let's get back up to the class. Right here, let's uncomment this part. We have, well, let's get back and actually uncomment this. So we have this uncommented. There we go. Here again we have, unlike the others, we actually have an enum. So it's an enumeration instead of a string or an int. And here we have these different class choices. Now remember, when you pick a specific image, the different classes you are shown will depend on that image. So here we have accessories, hair, necklace, pants, shoes, skin, vest, because of the specific image we have picked. Now let's say we pick this image here, it doesn't contain too many classes, so we'll take this and let's unselect this one. Also note that we're dealing only with one specific image. So we click on this one, and then you see here we have sunglasses, skin, shoes, hair, bodysuit, accessories. And this is simply because once we pick a sample, we go ahead and check out all the different categories which are found in this mask. So let's get back here and see how that's done. So for every, or for when we select a given sample, you see here we have our target view. See, context view, select. We select one. We have a given sample which we've selected. We then say, okay, for a given target view, normally we should select only one. So if we're going to go through this target view, and then we break once we're done with the first one. So once we select our target view, we go through the different samples. That's normally supposed to be 1 if we pick just 1. Then we obtain the mask. So for a given sample, we could get the mask by doing sample ground truth mask path. Read this with OpenCV. We obtain the mask, and then we now get the unique choices. So the unique, or we could call this unique categories. So what we simply do is make use of NumPy's unique method, which takes in the mask, and then we convert the values we get, because obviously if we have, say, class 0, we have class 23 and class 38, for example, then we want to convert this into their corresponding label. So we use id to label, and we take in this I, convert it, and then we have, for example, the background. But because we don't want the background, you'll notice that here we take from 1 to the end, because we always start with the background. Obviously for every image we would have the background. So that's it. And then we create this tuple which contains our unique choices. The reason why we're creating this unique tuple is because of the way the drop down type works. So it takes in this actually tuples. So that said, what we're doing here is we specify, or we create this class choices. That's it. We specify a label class, and then for all the different classes in our unique choices, we are going to add a choice, or we're going to add a specific class into those class choices. So now you see that it's only those which we got from the mask which we're going to add into this class choices. And now this is an enum, but the values we are going to have is gotten from this class choices. So we have class choices values. We have the default set to skin, and then the view is the class choices. So it's obviously this drop down view. So saying that the view is class choices, simply saying we want to have a drop down view, as we have seen here. So here you see we have this drop down view, unlike here where we have the slider view. So that's it. So for this one we have a form view. For this one we have a drop down view. For this other ones we have a slider view. We then return the property which takes in the inputs and the view. So that's it. So all these inputs we've been creating here is what we're gonna have. Now that's fine. We move ahead into the execution, or in our execute method. So in the execute method, which plays the role of our back end, we're gonna take all information from the front end, which is in our resolve input method, and then carry out the augmentation. So here we have number of images per prompt. You see context params, we get the number of augmentations. The default value is 1. So if you get back here, you see we have number of augmentation, num-aux. And then for the next, we have the selected class. You see the default value is skin, and then here we have class choices. So if we get to our class, you see here we have class choices, and then we get to the prompt. Again, here we have prompt, none provided. Guardian scale, the default value is 7. The name is guardian scale, number of inference steps, and then we also have the random seed, which is by default is 10. So that's it. And then we have our target view. With our target view, we are able to get a specific sample. So let's get out of this. When you pick a selected sample like this one, we're saying that our target view now is, because you see here we have 2. So our target view will be made of these 2 samples. So if we take this off and then we select this, our target view is made of only this sample. So for the sample or samples in our target view, we're going to do exact same thing we had seen already in the collab. So here we call on our transform sample method, which takes in the sample, the specific class, the prompt, the number of images per prompt, the guardian scale, number of inference steps, and then the random seed. So once we create these new samples, now unlike with a collab where we just pick the first one, here we could create multiple samples. So once we have these multiple samples, for each and every sample we are going to add this into our data set. So you see we add that sample, in our data set. Now the transform samples method isn't very different from what we had seen already, but we could take a quick look at that. So in our transform samples, obviously we have the samples, select class, prompt, and so on and so forth. Then we go ahead and generate inputs based on the samples file path and mask path. Then from here we have the Augment method, which obviously generates or creates our edited outputs. Then for each and every one of these edited outputs, here we have our list for each and every one of these edited outputs. For every edited image, we are going to save that, and then we're going to create a new sample. So that's why we have this new samples list here. So we create a new 51 sample, just exact as we had in the collab, and that's fine. So we save the image, we copy the mask, and then we create a new 51 sample. Then once we're done with this, we return the samples, and it's those samples which we use right here, and or which we make use of right here and add into our data set. So that's it. So that's fine. All the other methods which we call, like for example Augment, are found in our etils file. So if we get here, we have create pipeline, we have generate inputs, we have Augment, and then we have the create hash. So that's it. That's all we need to create a plugin. And so now we'll save all this and then push this code to GitHub, and then load or download our plugin and make use of it. Let's say instead our default random seed should be 100. So instead of 10, we want to change this to 100. So that's the only modification we'll make. Let's get back here and say our random seed. Okay, so we go from 1 to 1000, and our default is 100. Let's scroll down to where we had the random seed. Our default is 100. So we save that, and then we go ahead and push this to GitHub, and then download the plugin and make use of it. Once we push the code to GitHub, we could get back here and then download the plugins. So let's change this name. We have NeuralLearn, that's fine. Plugin name NeuralLearn, and we run this cell, and then now we could go ahead and visualize our data. As expected, we have different samples right here. Now note that we have 77 samples because we restarted our session, and because we are working with Collab, each time you restart your session, all the data is deleted. Nonetheless, if you're working locally on some cloud server, you wouldn't have this data deleted. Let's go ahead and check out our plugin. You see here we have Augment with Stable Diffusion Inpainting. If we get back up, you would see we have this other plugin right here, which is actually 51 plugins. Now this plugin permits you manage other plugins, like this NeuralLearn plugin we just created. So if you run this, you should have now the plugin manager added to our list of plugins. We'll need to refresh to have that. Anyways, let's get back here. We have Augment with Stable Diffusion. Remember, we need to select an image so we could carry out the augmentation. So let's select this one, and then we get back here. We have Augment. That's fine. Now notice how the random seed by default is 100, as we had modified it in the code. So that's fine. Our prompts, well, number of augmentations, let's say 10. The class, what we want to modify, the t-shirt. Then we have number of inference steps set to 50, guardian scale say 9, and then we have the prompt. Well, let's go ahead and copy again our prompt we just used. So data augmentation. Anyway, we had a prompt from here. Scroll down, we have, that's fine. So we replace boots by t-shirt. Get back to Vish, and then paste this out. So anyway, let's just copy that for now and look at the image. Well, so let's take off the ground truth. Okay, so that's it. Suppose we want to change this t-shirt into one that is, say, black, so it matches with this boots.
let's click again on that. So we select year, and then we have our prompt, a photorealistic photo of a man wearing a black colored nice looking t-shirt all black with white logo. That's fine. High resolution. Okay, so that's our prompt. We go ahead and pick our class. Yeah, we have t-shirt. That's fine. So let's run this. Let's increase this, and then let's go ahead and execute. Executing. We'll just wait for a while, and then we revisualize our data set. So when we go ahead and browse operations, you see we have this manage plugins, we have build plugin component, build operator skeleton, and then you should have this install plugin. So we've already seen how to install the plugin using the command, so we don't need to go through this. But if you click on this, you see you're asked to specify a GitHub repo, and then you could go ahead and install the plugin. So it's a plugin that permits you easily work with other plugins. Now, if we click on this manage plugins, you see we have neural learn data augment, and then we have a description here. So you could enable or disable the plugin. Then for the requirements, you just need to select the specific plugin you're working with, and you could see all the different requirements or all those different libraries which were found in our requirement.txt file. So that said, we could pick out say this image, and then now go ahead and augment. So let's click on augment, and then let's say we want to augment this say 3 times, and then we change the class. Well, we have a shirt, and we have belt, we have pants. There we go. Okay, let's pick out shirt, and then we have well, a photorealistic photo of a man wearing a, click on this, wearing a blue colored nice looking Gucci vest. Well, let's say a photorealistic photo of a man wearing a blue colored nice looking Gucci vest, or blue high resolution. Okay, so we have that. Now we could pick out any random seed. Let's say we want to pick out a random seed of 9 or 15. That's fine. Number of inference steps is 7. That's fine. Guardian scale 9, and then let's go ahead and execute. Once we're done with executing, we could now go ahead and check out the generated data. You can see the different new samples which are generated. You see it's actually resembling the prompt. It's a blue shirt. Though it's not very clear what's going on in this chest region, we still have something that looks like the prompt we put in. And then looking at the ground truth, you see all the zone, we have that shirt. We move to the next one. Let's take out ground truth so we could see the output here. This is quite fine. Ground truth, we have that. Now, as we have said already, there's a little bit of noise around this chest region again, because we expect the shirt to come right up like this. Anyways, we move to the next one. Let's take this off. Next sample. Well, we have a blue shirt, but it doesn't look very realistic. So, but at least it follows or it matches with the ground truth mask. We move to the next. This next one. Take off the ground truth. We have this shirt, which still follows the prompt, though not very realistic, but at least we have this blue shirt. Then we have the next one, which looks cool and also matches to some extent with the ground truth. So that's it. We just seen how we could generate new samples for our data set. You could go ahead and play around with this plugin, and then see how you could retrain a model with a much larger data set. So one good thing about this is that you could pick like this one, for example. You see we pick this one, and then we go ahead augment, and then we could say, for example, we want say 20 samples. So you could increase as many, or you could increase the number of samples in the way you want. Now let's see what happens when we change the person's skin. So let's get to the prompt. We have a photorealistic photo of an Indian man wearing a red colored, or well, let's say wearing a blue colored. Let's just say an Indian man. So let's take this off. High resolution. Okay, let's say a photorealistic photo of an Indian man, high resolution. Then number of inference steps 50, Gaussian scale 9, random seed, let's take 10. We have our newly generated samples. We have a couple of them. You see how we go from the black man to an Indian man. And one thing you could note here is the fact that sometimes the model generates the image with a long sleeve instead of a short sleeve. So you may want to delete some of the samples where we have the long sleeve. So like this one, we could delete this, delete this sample, and this one, and this one. So we're left with only when the man is putting on a short sleeve. Anyways, once you select this, you just get back here, Anyways, once you select this, you just get back here and then you type delete, and you have delete selected samples. So we execute that. With all the samples in long sleeves deleted, here's what we're left with. You could notice clearly the skin and even the race change. We've come to the end of the section. Thank you for getting right up to this point. If you want to continue learning, you could head over to neurallearn.ai and keep improving your deep learning skills.